Can you hear me? Yeah. Maybe this way? Oh, that's okay. So, dear participants, dear guests, it is my pleasure to declare the opening of the 14th conference ICTERI-2018. I can say that this is an important date for us because it demonstrates how conference is growing from year to year. Many people for many years contributed to the conference. Let me introduce the members of the steering committee and program chairs. You know that the general chair of the conference is Professor Alexander Spivakovsky, but he is an extremely busy man. He called maybe 10 days ago and said he do the best to come to the opening. But in 2 hours, even less, an hour and 30 minutes, he had to present the new law in the parliament, and so he has no possibility to come here. He sent his warmest regards to the conference. Professor Heinrich Mayer is a person who I can call a tutor of the conference. For many years, he teaches us how to improve the quality and go from one level to another level. Professor Grigory Zhulkevich represents the second capital of Ukraine, Kyiv, big scientific and industrial region. He always, let me say, closes the gaps in the conference. If it is required to be a chairman of workshop or chairman of young scientists and so on, Professor Zhulkevich is always ready to do this. I would like also to present the authorities of our university, the Vice Rector, Alexander Roshko, and the Dean of our faculty, Professor Anisimov Anatoly Vasilyevich, and two chairs of program committee. I would like to say that this year we have enormously big number of submissions, more than 200 authors, and Professor Anisimov, for example, should sign 250 certificates and 300 invitations. It's a big job, of course, but not only such a job we did, and you understand there's several hundreds of submissions is enormous number for reviewing, times, and so on. So, the Marie Carmen, Professor Marie Carmen is program chair, and Professor Vladimir Malayev is co-chair, second chair, if you like. Professor Malayev is the engine of the conference. Without his efforts, probably it will be very difficult to do something. I will not go into details, and in the speech of Professor Malayev, he will describe sponsors of the conferences. So now let me ask our members of program committees and chairman say a few words. Please, Henrik.
Thank you, Vila. Good morning, ladies and gentlemen. I'm very happy to be here again. ICTERI has now quite a long history, and it's a history of increasing success. And in particular, what I'm really happy and a bit proud about is that not only the contributions improve, so that it's becoming harder to select the papers for the conference, but although the way how the papers are presented is fine, and now most of you who are presenting know that this year my task was to check the presentations, and also those became much better than it was some years ago. So I'm very happy that the conference now is becoming a standard. And this is my hope for the next years, will attract also more and more international participation, because that's important, namely to have colleagues from everywhere that are working on these topics, to be able to discuss with them and to exchange opinions, and also that they are more and more looking at your works that you are doing here. And I think there is enough good results of research here in Ukraine that merit to be spread internationally. So that's my hope for the next years, and I'm now looking forward to a very nice conference these days. Thank you.
Thank you. Professor,
last year, we begin our PhD symposium at ICTERI conference. It's a very interesting event because this event gives a chance for young scientists to present their ideas, to present themselves for scientific community. For me, it's a very pleasure that participants of our PhD symposium of last years are the participant of main conference in this year. So we see the progress of young scientists. It's very important in this time because ICTERI is one of platform for presented young scientists for obtaining possibility to present own results for wide scientific community.
We are very grateful to the Russian International University, the gold sponsor of the conference, who gives us a nice condition. So let me ask Professor Alexander Rushko to say greeting words from the US.
Шановні колеги, дозвольте передати вітання від ректора нашого університету Леоніда Губерського з початком конференції, з продовженням конференції. Нещодавно вийшов звіт Римського клубу щодо нових тенденцій світових глобалізаційних по технологіям, капіталізму, народонаселенню, кризі. І, як свідчить цей звіт, темні сторони цифрової економіки мають так само певні вияви. І ці вияви проявляються в тому, що нові технології і їх спрощене використання інколи абсолютно не дають можливості, чи можуть не давати можливості пошуку нових рішень, складних рішень. І, як на мене, саме така конференція, вона дає змогу об'єднатися науковцям світу для вирішення таких проблем, для створення нових моделей управління різними рішеннями і, звичайно, сприятиме кооперації університетів, створенню певного такого наукового нетворкінгу, який буде сприяти, звичайно, зростанню рейтингу нашого університету, співпраці і відповідним результатам. Дякую всім учасникам, гарних результатів, комунікацій, спілкування і до наступних зустрічей. Дякую.
First of all, just a few words. I would like to greet you. I would like to greet you here at our university. We are living in a very interesting global world, and we are moving to digital world. And I think that main players in this world are zeros and ones, and we must control all these flows of zeros and ones. Therefore, we gather here to discuss, to invent new algorithms, methods, programming languages, and etc., etc. Topics are very, very important because education, research, they are very, very interconnected, and also industrial applications are of great importance. Therefore, I wish you very fruitful collaboration, very fruitful ideas, new exchanging ideas. I wish you success in all your deeds. Thank you.
Thank you very much. Last but not least, the program committee chairs, Marie and Vadim, please.
Okay, thank you very much indeed. I will do myself not to bore America. May I please ask you to switch on the beamer? The beamer, please. Thank you. I will draw your attention to more practical things. I'm fully seconding all the greetings you've got from nice people sitting here that proceeded. But I think that our service, our community service, is to be also very useful for you. And I think that this slide, giving some key facts and figures and numbers about the conference, highlights that we've been useful and quite successful this year. So we've got 251 paper submissions from the authors coming from 23 different countries in the world, not only Europe, but also Asia and Americas. We have accepted 107 contributed papers with the authors coming from 19 different countries, Europe, Latin America, and Asia. We've got 4 sponsors. We have 290 registered participants, which is almost 100% increase compared to last year, from 13 countries, and also many unregistered as usual, like local students and people coming from different research departments here at the university. As for the program, we have 2 keynote talks, 1 invited tutorial, 4 thematic tracks, a PhD symposium, poster and demo track, 5 workshops, and perhaps industrial IT topics. As you well know, ICTERI is an international conference, but it's also a peer-reviewed conference. That means that acceptance has been decided based only on the expert reviews. So speaking about the program committee, it was really composed of experts coming from 29 countries, 197 top people in their fields in total. And this is the distribution per country. You may come and look at those slides after offline if you wish to have more detail. So overall, speaking about the submissions, we have seen 240 contributed papers and 11 workshop proposals. We overall accepted 107 contributions and 5 workshops, so the acceptance rate averagely was below 50%. Here you may see the details on different sub-events in the program. The program itself is available and easily accessible using QR scanners in your handies. So you scan it even now here and get access to the program, which is available online. Our keynote speakers represent a very nice constellation of different capabilities, different fields, and are coming both from academic research and industrial research. This is always the way, a traditional way for ICTERI to invite people to give their keynotes. But Stephen Lawton, a senior researcher at the Fraunhofer Institute for Intelligent Analysis and Information Systems, will talk about augmenting educational material with knowledge graphs. And this keynote talk will start immediately after we finish this official opening session. And our second keynote speaker is Professor A.Horoняк, a professor of information technology at Western Norway Research Institute. He will speak about unlocking value from ubiquitous data. Now, we also have an invited tutorial describing and teaching the participants to use the platform, which is becoming more and more popular in the academic community. This is the slide reader step. And the tutors are Klaus Andreas de Graaf and Benjamin. As for the proceedings, this year, due to the bigger number of papers, we've decided to publish not 2 but 3 volumes. One contains the papers, the contributions for the main conference, including posters. The second one contains the workshop papers. And the third one is for the PhD symposium. The links to the proceedings in their preview form are given here, and of course here. So we scan it and look at the proceedings at the website of ICTERI.org. As you know, the proceedings will be published after the conference when we clean it up and delete the no-shows. So as for the post-proceedings, we do traditionally publish it and will publish for this conference instance, which has already been endorsed and approved by Springer Nature. The estimated out of print is the first quarter of 2019. Speaking about the socioeconomics, you well know that ICTERI is an international conference. So, as far as we have people from 13 countries here, you may subsume that not all of them understand your native lingo. So, the papers must be presented in English imperatively. The PhD symposium language is also English, so the same rule. The poster and demo track language is English, so the same rule. Except the workshops, who take care about the languages themselves. Those are the sponsors, and the information could be scanned and overviewed in details. And of course, I would like to thank the fellows, the big team who did their best to deliver you the best community service they could. Thank you very much, and I wish you a very pleasant and excellent instance of the ICTERI conference this year. Thanks.
Well, you have 5 minutes break. And then we start our regular sessions.
Дуже приємно. До зустрічі.
Yeah.
Okay, so good morning, everyone. I think we can start with our first keynote. It is a real pleasure for me to present Stephen Lohman, that is a senior researcher in Fraunhofer Institute, and also is working or teaching in the University of Bonn. He's an expert in knowledge management and semantic web, and is working in different research projects and industrial projects also. And he's going to present our vision, a vision about how to use or to apply knowledge graphs in educational context and also in industrial context. And the title, as you can see, is Augmenting Educational Material with Knowledge Graph. And please, you can go ahead and explain your vision about that. Thank you very much.
I tried that one, so I'm not you. So thanks, Mari Carmen. Yes, it's a pleasure to be here and to talk about knowledge graphs. Yes, who have heard about knowledge graphs before? Okay, who have heard about the semantic web? Okay, yeah. Who have heard about computer science? Okay, so I will give a bit of introduction to knowledge graphs and semantic web and related topics, so that I think everyone will be on the same page. We do a lot of semantic web research, we do a lot of research on knowledge graphs, but I think it's important to understand the basics first. So, what are knowledge graphs? I think everyone here knows graphs. You have graph theory. Many of you showed up for computer science, so many have a background in graph theory. They might have already visualized graphs, represented graphs, did some algorithms, applied them to graphs, and they use Google. And that's if you Google for Kiev, what you get as a result. Nowadays, no longer just a list of topics. So before it was like that, just keywords, search results, and a list of topics. But nowadays, you get quite sophisticated information about Kiev already. So let's use a pointer. So on the right you see information about Kiev. Here you see some news about Kiev, Twitter data about Kiev. So you have a lot of structured data, you have a lot of information here, not just a search result with links. So that's what we call shifting from a web of documents to a web of data. Which means before we had documents and hyperlinks, we still have it, it's working fine. But more and more we see something like connecting things, connecting entities, connecting people, connecting cities, persons, and with typed links. So with some more information, with some structured information that we can do nice things with. This is a Wikipedia entry of Kiev. As humans, we can read it nicely. We see here basic information, we see structured information, and especially the structured information is what machines can read and interpret. This is a bit harder to read for machines, it's also possible, but this whole website is designed for humans. If we now want to become more intelligent, if we want to have more intelligent machines, we have to change it in a structure that machines can understand. So, what we call structured data, semantic data. And we use it and can extract it. There's something called DBpedia, and we can see all this information in Kiev that we found in Wikipedia we can see now in a structured format about the population, about the latitude and longitude, about birthplace of people who were born in Kiev, prominent people, which are also on Wikipedia. So we have entities like cities, people, and others, and these things can even be opened up, and I have to go downstairs to my laptop for it. So whoever wants to take a look, just Google for Kiev. Okay, it doesn't work because internet connection here is not always, but you can check yourself under this link, and then you see the structured information. So what can we do with it? If we have the structured information, we can represent it as facts. Basically, this structured information are facts. So we usually use statements. That's what we call RDF statements. So for those who know the semantic web a bit, that's a bit of a basic introduction. It's important to understand that this information is represented as subject, predicate, objects. And if we have some of these statements, like in this case Vitaly Klitschko being the mayor of Kiev, Vitaly Klitschko having a birth date at that one, then we can construct a graph. Which means from these statements, of course, we can construct a graph where Vitaly Klitschko is now here in the center. He has a certain title, certain birth date, and other information. Where do we get this other information from? Once again, DVpedia, or some similar structured data set on the web. Here we see an abstract about him again, and structured data, where he was born, which party he belongs to, and so on. All automatically extracted from Wikipedia. And we come up with a larger graph, where we see, okay, Vitaly Klitschko is born at that date, the mayor of Kiev, has this birthplace, which is in this country, so he's not from Ukraine, we learned already, and he is a person. That looks quite natural. Of course he's a person, but for machines this is important information. And for interpreting this data, it's also important to know he is a person and not whatever, a car, a building, the place, or whatever. And he's a politician. And you see here, those who have an interest in object orientation, you see here multi-membership is possible. So he can be at the same time a person and a politician, of course. He was even a former sportsman. So all this information can be saved in one graph. And then we get this information, and at least I, until I prepared that, wasn't aware that he's actually not born in Ukraine, but in Kyrgyzstan. So this was a bit of new information for me. So we can learn from these graphs. So we can not only learn from these graphs, we can do cool things. And that's why we call them knowledge graphs. If we have this structured information extracted from Wikipedia or given in some other resource, and we have it nowadays, we have a shift from a web of documents to a web of data. And that's what you experience if you use Google or some other search engines today. So if you ask Google, and that's called the Google Knowledge Graph, if you ask Google how tall Vitaly Klitschko is, Google will give you the answer. Who knows how tall Vitaly Klitschko is? Okay, I asked Google, that's why I wasn't aware about it before, but he's 2 meters, nearly 2 meters and 1 centimeter. So that's the result. And I really asked Google, how tall is Vitaly Klitschko? So if you enter this in Google, you get that information. And nowadays, you know, with these agents, so everyone have heard about Alexa, maybe some of you have it even at home. I have Alexa, this Amazon assistant. At some point my wife was complaining because I talked more to her than through Alexa than to my wife in the beginning, and then at some point it decreased. But if you have this information, you can ask a machine, a virtual assistant, even natural language, some question, and you get a result. Like in this case, about Vitaly Klitschko. You have structured information, you have the answer, you ask a question in natural language. That's one opportunity. And I think that's something which is at at the moment very much researched, and there's currently a certain hype on these topics of having really natural language conversation with agents. So who followed the news, there was now Google I.O., and they introduced this agent doing telephone calls, really asking questions, replying to questions, answering to questions, as we as humans can do. And this is only possible because they have world knowledge, so they have an understanding of the data. They have an understanding of what they should ask and what information they need. But this is limited. This is limited to certain domains. Still, machines, even if they have the structured information, are not as intelligent as humans, everyone knows, but if they have that structured information, they already can do nice stuff. For example, answer such questions which are hard to answer for humans if they don't know. This is an example of what we developed some time ago. It's also based on a knowledge graph. So here, yesterday I entered Vitaly Klitschko and Kiev and found some nice relations. So this is what you can do with a knowledge graph. You can't do on the web. You can't Google for two things and get connections. But here you can Google for two things or enter two things in the search and you see connections. Maybe this works live, let's see if there's internet connection, because it's much more impressive if you see it working. Let me do a trick. So I'm connected, but you are no longer connected. So this is called the Rel Finder. Just Google for it. That's a tool we once developed. You need, in this case, a flash player. Okay, I thought that the internet connection might be slow, so let's move the prepared version. Here you see, which I already entered, Kiev and Vitaly Klitschko. Of course, you can also look for things of Kiev and, for example, Bonn, where I was coming from yesterday. And then you can also find relations between those entities. So you can use it even between 3, 4, 5 entities. You can look for relations. It's no magic, actually. It's just computer science. We have the knowledge graph, and we enter 2 or more entities, and then it does a breadth-first search. So you just go from both sides of the graph of the entities, go through the knowledge graph, follow those links, and then you see connections, for example, that there's some person, and we have further information here, who was born in Kiev and now his residence is in Düsseldorf, which is close to Bonn. Or there's another one, another city called Cologne, and another person. You might know those people. I don't know them, and if we don't know them, we can easily look information up. Here on the left, extracted from DBpedia in different languages, so even German or whatever languages are available for these people. We can even filter. We can say we're not interested in everything. For example, we're not interested in cities, we're not interested in countries or roads, we're just interested in, here we see, in chess players. That if we look for chess players, and there are 2 resources which are now not shown by label, which are related to chess. So you just try yourself, maybe with a faster internet connection, just Google for Rel Finder and try what's possible with these knowledge graphs. So what's under the hood? What's below these knowledge graphs? And that's why I asked in the beginning, who knows about the semantic web? Basically, there's explicit semantics below the hood. There's semantic technologies below the hood. Of course, Google is not using what we use in academia. It's using a bit of proprietary own format. Of course, Amazon Alexa is not using what we use in academia. But in academia and in the open world, in what we think is the right direction, we use especially this semantic layer cake. We call it the layer cake, not because it looks like that. It originally looked like that, and then some guy said, I bake it. And it's already quite some time old. So it was invented in 2000, which is roughly 20 years soon. There was a vision of the semantic web by Tim Berners-Lee, the inventor of the World Wide Web, and he said we need more a data web. And as always with innovative ideas and visions, this takes time. And I think at the moment we're somewhere about here. So the stack remained more or less the same, the layer cake, but we have a bit changed maybe the technologies. So 20 years ago, XML was basically the standard. Still, we use a lot of XML for data exchange, but we use more and more JSON, especially on the web, because it's a bit more efficient, smaller in transmission size, and so on. We also have something like CSV, tables, spreadsheets, that we can convert and expose to the web. So that's another format which is used, actually, and then converted into RDF, or databases, or even embedded semantics in a website, which is popular. For example, microformats were quite some popular in HTML5. There is more explicit semantics. So let's go back to this explicit semantics advisory. So we have now explicit semantic included in HTML code, more and more that search engines can use it, interpret it, and then provide more intelligent results, more intelligent search, and so on. On top of this, like the stack goes, as usual, from the very bottom to the very top. The top notch is logic. So if we have knowledge, we can do logic. But we can only do logic, we can only do reasoning, we can only do inferencing if we have proper knowledge below, or beyond that ontologies in the whole stack. That means we can apply rules, logic rules, we can apply logic if all these below layers are met. We need URIs. So before it was URI, nowadays it's IRI, International Resource Identifier. So we are allowed to use more characters there, having different languages, Ukraine language, or Russian language, or Asian languages. We have, as I said, more serializations, but we don't care because we have this integration layer which is called RDF, Resource Description Framework, this subject, predicate, object logic that I presented in the beginning. Very straightforward, very easy, basically, as it's like we speak. We speak as subject, predicate, object, and they can be combined to these graphs, and they follow certain schemas. So, if we have this knowledge, I already showed, we can ask questions like, what's the size, what's the height of Vitaly Klitschko? Or, what's the population of Kiev? So, I was also surprised to see that Kiev is eighth biggest city in whole Europe. So that was new information for me. I learned from these knowledge graphs. We can do even more sophisticated query. For example, this is a still rather simple query. Here we looked for people who were in a movie, starring in a movie, together with another person, and the other person was the child of that person. So for example, there were results like Will Smith playing with his kid, or I don't remember all results, but we see here from the bubble, it's more than 100 that could be found just on Wikipedia, where parents start together with their children in a movie. Or we can ask another question. So everyone knows Barack Obama, but I think few people know which universities he was having his education at. And there are other people. We found 18 which had the same university, or which were at the same university, and who also belonged to a political party. So for a journalist, that's quite interesting. Journalists can look up at these people, maybe, and find some relations and see what they are doing now. So I think you can ask much more complex queries. So this looks actually in Sparkle, which is a language for querying knowledge graph. It looks like that. So a bit complicated. Not everyone speaks fluent Sparkle, but you can use such tools, visual tools, or learn it, and then you find information which can be quite complex based on these knowledge graphs. It's an open world assumption that we follow usually, so we cannot say that these are the only 18 people, at least if we ask the web. But in a closed world scenario, in some, for example, university context, at this university that's a closed world, we know all its members, we get even very precise results. We can do queries, which we usually can do similarly on databases, but what's very nice and different is that we have typed links. So we not just know that there is some relation, but we know of what type this relation is. So we can query knowledge graphs, and for that we need schemas, and that's something I just added yesterday because you said you like ontologies. No, I'm kidding. So ontologies are very important here for knowledge graphs because they structure the world. They tell us what's the person, what's the date, what's the nose relation. So all this is important to know, and we have it in ontologies. And there are a lot of ontologies out there. So they usually look like, let's switch to this one, like that one. That's a kind of beautiful visualization of it. And once again, I try to open it on the computer, so you can just go to the web and check if it works. If it's not working, just switch to, I often prepared it. So that's the ontology about people and agents, what we call them, and their relations. So for example, agents have a weblog, that's a document. Agents, usually people, so persons, it can be a person, a group, an organization, they have a certain age, they have a gender, they have a maybe status, a Skype ID. So all this information, you know it from data structures, from database design, is in these ontologies. This is a rather small example. Of course there are larger ones or even smaller ones. And they have a family name, a geek code, especially persons, they have an image depicting them. So you have all this information which is represented, which we as humans, of course, are familiar with, but which we have to train, which we have to use to describe the data. And that's what we call knowledge representation, and that's what we use ontologies for. So there are already a number of examples out there. So you can look them up, for example, in the linked open vocabularies website or in the bio portal if you are in the bio domain, especially in biology and biomedicine. There are a lot of ontologies that structure the world, that help to find common schemes so that not everyone designs his or her own scheme, his or her own database scheme, but that people are using the same schemes, which of course helps to exchange knowledge, to represent knowledge in a unified form. And here, for example, you can see DC terms, the Dublin core vocabulary is very popular. It's a very small vocabulary describing documents. So you can say, for example, who's the author of a document, or when was the document created. All this is very basic information, but we need it in a structured form so that everyone understands it, including machines. And the more people use these common schemes, or what we call ontologies, the easier it is to interpret data and to really make use of structured data. Okay, I think that's what you need to know about ontologies. That's what you needed to know about the semantic web. And that's what you need to know about knowledge graphs. And here's another very popular schema or ontology called, you find it on schema.org, which is used by search engines to search for semantic information on websites. So it's basically a large hierarchy describing different entities. You can describe products, or you can describe places or people. And what's important is if you structure your data on your website using these semantic information, this can be automatically done or you can manually edit, then search engines like Google, Yahoo, Yandex, all the big ones, understand better the data, understand better your website, and can make more intelligent suggestions, recommendations also for users. Especially in product search, this is of course important. If you have a product, if you want to sell some device, some good, you describe it as properly as possible so that it's found on Google, that people can find it, and not just on Amazon or other centralized services. So the whole idea here is to have a very decentralized world, so in the original sense of the web, to not have centralized services like we nowadays have Facebook, Amazon. Of course, those services also use semantic information, but the good thing is, once again, bringing the power back to the people, bringing the power back to everyone who adds information to make more use of this information. And this everyone approach is important, because if every one of us tries to develop, to design his or her own world, that doesn't work. At the moment, there's some, let's say, politics in the world where people try to design their own world, but usually the world works if we exchange with others. And for example, this is an example where we represent Bob on his website, and Bob says he's interested in the Mona Lisa. But instead of just saying the Mona Lisa, he links to the Wikidata source of the Mona Lisa. So Wikidata is something similar than Wikipedia, where there's already more information about the Mona Lisa. So we know what's about, by whom it was created. So it doesn't make sense that Bob enters all this information about the Mona Lisa on his website or in some other form, but it simply links to a data source, the Wikidata, where this is very properly described. He might even add other information, other knowledge. It's not yet in Wikidata. And if everyone does, of course, then it's much easier, and we have nice knowledge graphs, because everything gets linked to everything. And that's the result. So that's the current, what we call the linked open data cloud. So we have a lot of content that's generated in different domains. A lot is user-generated. Of course, we have social networks, we have publications, we have linguistics, life science. Life science, you can see a large area here. As I said, biology likes to structure knowledge, biomeds and pharma industry. We have geography and others, and they are all connected. So if we look into the nucleus of this linked cloud, we see that there are many different data sets that are interlinked. In the middle here, Wikipedia, in the center, GeoNames, which is for geodata, FOF, which is for social data. We have all this data openly, and that's the idea of linked data, linked open data, openly on the web. Of course, it's hard to get every data openly on the web, but especially common sense data about people, about Vitaly Klitschko, about Kiev, or also about Bob and Mona Lisa, or different other examples, we can make publicly available. Geodata that's extracted from OpenStreetMap. So we have this data also on the web. So we can go to Kiev, we can go around in the city, and we have this structured geodata, and it's already available. All of you use Google Maps, some might use OpenStreetMaps. We have structured data, and we just have to link it with other data, and we are much richer in understanding. And that's the basic idea of linking data sets to really, see relations, and if we stop by whatever, a site here in Kiev, we get even more data from Wikipedia in the DBpedia format, maybe even some profiles of people who live in an area. So all this, what we know from centralized services nowadays, which are owned by companies, and the idea behind the linked open data is to make as much as possible of this information publicly available, so that everyone can use it, every service can use it, and make some benefit from it. Especially for, as I said, information about cities, information about countries. This is very much available because in many countries the governments should publish this data openly so that citizens can see, for example, where they spend the money and so on. That's what we call linked open data, and that's the guy behind this idea, this vision, Tim Berners-Lee, and it's very important just to understand those basic principles. So we want to use URIs or IRIs to make things available on the web. So it's always good if everything has a URI. Then we can enter those URIs in the browsers and get information, either for machines or for humans or for both, which we need content negotiation. So you just enter the URI and you get information back, as I showed for Vitali Klitschko. Then, of course, it's good if we looked it up, if it's not just a human-readable website, what we have nowadays already, but if you have also RDF data or machine-readable data, structured data. And then, and that's the last step, the idea of linking stuff, linking entities, to not just have this isolated information, but really having a knowledge graph. To do things, as I've shown with the rel finder, to do a breadth-first search on this graph, to find connections, to understand relations better. That's a bit of what's important to understand about knowledge graphs, semantic web, linked data. Not all of this is working, much of this is vision, but I think some things are really working cool, and that's what I would like to show in some applications. How you can apply this to really make use of knowledge graphs, make use of the structured data. So, if we look at applications, this was a project we once did, where we just used books, did some text processing on books, so natural language processing, and tried to find as much information as possible in a structured format, in a knowledge graph representation of these books. So we did, whoever of you is a bit familiar with knowledge, natural language processing, we did some tokenizing to isolate the words, we did some sentence splitting to find different sentences, and named entity recognition, which is important to identify entities in the text. For example, Mr. Fogg, Passepartout, Fix, Sir Francis, and so on. That's a novel around the world in 80 days, which some of you might know, and then having this knowledge extracted without reading the novel, without understanding the novel, as a human, we can already use the machines to generate something like that. So, once again, a bit of a visual representation. So we see how much occurrences of Mr. Fogg are there in the text. He occurs quite often because he's a main character of the novel. We see which other people occur or which other locations occur. So it seems to be London, Hong Kong, Passepartout and Fix. Here we see a network of main characters from the novel. So Mr. Fogg, Fix, Passepartout, Ayuda. And the nice thing is, if we even use it on a chapter basis, we see a bit of the novel story. So this is like we find out automatically generated, and this was not manually tuned, that Mr. Fogg and Passepartout Stuart and Rolf started in chapter 1 Fix, but then, for example, Ayuda just comes later. So it's an interactive example. If I would click on this, I would see which chapter. So she appears the first time in this chapter, and then she stays with, if we follow the blue line, with Mr. Fogg. And in the end, she disappears or whatever, and Stuart and Ralph, and who knows the story, and I looked it up then. Stuart and Ralph, maybe let's see. Okay. So that's a different clicker, and it has a nice feature, being black. So maybe I continue like that. So no, to get back, so we see the whole storyline. For example, they did a bet here in London, so we can even put the place maybe there, and then after these 80 days, they meet again, and then they see if they won the bet or not. So whoever knows the story can make some understanding or understands a bit the storyline graph, which was, as I said, automatically generated based on the extracted knowledge from the book. This is another very popular novel, The Lord of the Rings, and once again, extracted from the book. We have a lot of information already, like how much certain characters interact, like Sam and Frodo here, which characters interact less, but still interact. So by the size of this edge, we see how much interaction there is. We see which are the most popular or most important characters and other information that is extracted, other words, and we see where they appear in the novel. So just based on entities, on information about entities, we already have a good understanding of a novel we have never read. At least we have an understanding that we can do some analysis on it. I call it, or we call it, distant reading, so we don't have to read the novel, which is of course nonsense if you really want to understand the novel. But if you analyze a lot of text, a lot of different novels, a lot of different documents, it sometimes makes sense to just do statistics, analysis, and knowledge entities, extracting them, understanding them. What's missing here are the typed links. And that's the power of the knowledge graph, and that's really hard, as I said before. That's really hard with the difference to databases, getting those typed links. So do not just see the relation, but also see what type its relations of. So that would mean another step in natural language processing, where we try to find out, for example, based on verbs, on adjectives, how they are related. This is, we applied similar technologies of natural language processing to different domains. This is a patent domain, so whoever filed a patent knows that's a hard deal, and whoever read a patent knows this is really hard to read off. So we also tried to once again get supported by natural language processing, by extracting entities, and even constructing ontologies. And that's why we used here not just term extraction, but also relation identification, so type links, as I said before, between the different elements. We used the GATE framework, which is a popular NLP framework, and we used Neo4j, which is a graph database. So the current trend of going from normal databases or linear sequential databases to graph databases, to connected databases, is very powerful for knowledge graphs, because then we get the links. And here we use a graph database. We could also use a triple store, what we call a triple store, but here we use Neo4j. And then we can visualize what's in the patent. So, for example, here there was a patent about I think a toothbrush. So we get the individual components of the toothbrush, the relations, how it's mounted, that it has a motor, an inner motor, that it has some brushes, of course. That's an electronic toothbrush. All this information we could extract from the patents, and we could represent as a knowledge graph. That's not, for one patent, that's maybe not too powerful, because we can read the patent. The problem is, if we do this for several patents, that's quite time-consuming and quite difficult. And that's why, with extracting this, we get a lot of information. For example, here, which is another visual tool based on the knowledge graph, where we can see what's the trends in patents, what are the companies filing those patents, what classifications they belong to, and get all this information, also the extracted keywords or the entities even of patents. And you can imagine that this is much more efficient to to use such an interface than really reading through all the patents individually and trying to find out what's in the patents. And nowadays, this is something which companies really care, because there's a lot of patent filing, and if you miss a certain patent, a very important patent, which is attacking your product, then you are in trouble. And that's why companies pay a lot of money for patent lawyers to really read the patents, to write patents, and that's why such analysis software based on semantics, based on relations, the more semantics the better, can help doing this job and maybe limit the amount of patents that has to be analyzed. So here's another ontology, since I talk about applications, and that's an ontology about technical standards. So here, for example, we designed a standard and relations between standards. A standard has a certain domain. It has a classification. So all this information which is in a standard can be represented in such an ontology. And if we do, we can once again see relations between standards. And that was another domain issue, so we had a lot of standards here and relations between these standards. And it's hard to get an overview, it's hard to really understand how these all are related. So we have this in the knowledge base now. Unfortunately, as I said before, once again, just a related to link, so not further qualified. This is, of course, little information. We just know these two are related. It would be better to understand how they are related. But once again, this is a knowledge graph that can be represented as a graph. Here it's just the related to links, so no real type links, a bit of typing, we know they are related. And we have these explicit relations. And now comes a bit of what you can do with reasoning on top, or inferencing. So if you then apply reasoning, then you even find more relations between these standards if you not just look what's in the knowledge base, but what you can infer from this knowledge by following other links, by following relationships. And if then, in the last step, you not just do reasoning, but also include external knowledge, then you come up with something like this. This is, of course, not readable, but you see it's a very large graph. So we used DBpedia again, we used other knowledge sources, which blows up the graph. You have a lot of linked knowledge, and you have a lot of relations here, even to external entities, even to external information about standards, which is available on the web, but which was not available in the data set we crawled. So now you see a bit what's the benefit of having external knowledge available, like DBpedia and other sources. So you can come from what you modeled here, from your knowledge, from a data set, what you find, to do some inferencing, and then using external world knowledge to really come up with something really huge. And that's, of course, once again, very nice. I would like to give another example. So I prepared some example. Let's see if it works this time. To just show that a graph is nice, but this visualization is not really useful. So you can zoom in, but in general, we try to not visualize such large graphs, because it doesn't make sense, you don't see anything. That's why you usually then use something else, for example, such visual interfaces. Let's see if it works. So this is just a very recent prototype we developed, not yet fully filled with the data, but you can say, okay, because I don't understand the knowledge graph, let's go to different dimensions. What you often have in data is geographic information. So you can just go to map visualization of the standards and then try to find out where these standard organizations are, for example, based. Once again, not working very fast. Let's see if the time thing works better, because it's doing some Spark querying in the background. It needs some internet connection. Here we go. So that's the world map, and you can, for example, see where certain standard organizations are based. That was the interest in this project, to see, for example, where the ISO, where the IEC, where IEEE and other organizations are based, which cities, and so on. So this is straightforward. We use maps for geographical data. If we have time data in a graph, of course the natural thing would be to use a timeline. And that's why it's important to understand. I showed a lot of graphs visualizations, but basically this information is differently structured, and we can use timelines to find out when certain things appeared. For example, there was an oasis in the early 90s, the DIN, which is the German standardization organization, quite some history, 100 years now. And then there's a W3C, like the World Wide Web Consortium, created just around 1995. So we have this overview on a timeline, and of course we can still have this knowledge graph. We have it in the background, but we don't visualize it here. This is just a hierarchical structure, so we can zoom in, look on these standards, and get more information. For example, for this IC whatever, design of graphical symbols for use in technical documentation, and then we see here, and that's basically the ontology, including this visualization, which I showed before, about the standard, about organizations, the standard developing organizations, which are linked to external knowledge again, so the dark blue is external knowledge, and you can scroll down and you have all the structured information, not as a graph presented here, because humans have sometimes trouble reading graphs, but really having a structured document where you see that there are standard licenses, which licenses are there, and this information can once again be linked to external resources. So I don't have to design an ontology on licenses, I just link to an ontology of licenses, and then I see or get already information about these licenses. So, where was it? Yes, so that was the landscape. So what I wanted to show here is that it's not, because it's the graph, you have to visualize, represent it as a graph, that's a natural thing, but often you have different dimensions of data which you then can provide to the user. And so you can have hierarchical views, geographical views, timeline views, and they are not too difficult to generate because they're good web APIs that you can use. So for example, we used OpenStreetMap for the time view, for the geographic view. We used just some other D3 component for the timeline and mapped the data to these dimensions. I think everyone knows from data analysis, everyone knows from data science. The difference here is that we have structured data. This can even be automatically generated, so we don't have to invest much effort in mapping it to a certain dimension, but we can automatically show it on a map or show it on a timeline because we know it's about geographic information or it's about time information because this is encoded explicitly in the semantics of this data. Now in the beginning I said education. So why is this important for education? I think we already learned that everyone can learn a lot by just using these knowledge graphs. That everyone can learn a lot by Googling information nowadays. Because we have structured results. This is something I wanted to introduce today because it's another project we are currently working on. It's SlideWiki. And there will be a workshop this afternoon about this environment. The basic idea is that we have a platform where we share slides. So today I present slides and I still use PowerPoint because of the internet connection, which I'm not too sure about. But you can also create those slides with PowerPoint or other tools, but you can use SlideWiki and even collaboratively create them. A bit like Google Slides, if you're familiar with. The difference is there's a lot of social features around, which are especially for learning purposes. So you can structure your slides, you can tag them with educational tags also, or topic tags. You can discuss them, you can ask questions. So we especially use it, for example, in lectures about the semantic web. Our semantic web lecture is on SlideWiki. and student can directly ask questions about those slides. So we have the authoring of slides, the change management, which is very nice because if a colleague of you does a change, you also get the change, and so on. So very collaborative environment to create slides on the web. And since it's on the web, since it's not PowerPoint, we can do something which I showed before. We can do natural language processing, we can do knowledge extraction, entity discovery, and we can create from the platform itself or triple store, which allows for linked data interfaces for structured queries. And once again, for those who have an interest in natural language processing, or for those who want to become some interest in understanding, we have HTML, we have the website, which is always first converted into text. So to extract knowledge from web content, it's important to code to text, or to already use the semantic information which is on the website. In the next step, we do language detection. This is especially in SlideWiki, which is a multi-language platform. That's important that we just identify which language the slide is in to use the right tokenization and entity recognition. You can see here some languages are supported already, not too many, but this shall improve in the future. So we have a tokenizer, tokenizing, like finding the different words. We have once again named entity recognition. We use a public library, it's called OpenNLP, which is an Apache project, very nice to do that. Here we use some other tools and libraries, and then we do a TF-IDS, so term frequency, inverse document frequency, to find the really important terms which are not on every slide. And then in the end we do something which is called DBpedia Spotlight, where we map those entities that we found in the slides to DBpedia resources, so that we get even this external knowledge which I mentioned before. Yes, if we run all this pipeline, we get some nice knowledge from it, we get some understanding of the contents, and we can use the structured knowledge, for example, for automatic question generation. That's a feature that's not yet integrated in the public version of SlideWiki, but we designed, developed. It has NLP under the hood, and we can create something like this automatically from the slides. Which means, in our so many web lecture, as a lecturer, I don't have to invent any multiple choice question. I just run the system and it gives me some questions that the students can then fill to see if they understood the text of the slides. Once again, it's more about common world knowledge so everyone understands. So the Eiffel Tower is located in, and then the difficulty here with the knowledge graph is actually not to find the right answer, which is Paris, but to find good distractors, to find good other options which could be answers, realistic answers to this question. So, for example, Danube is a river would be the right answer, but you see already it's not that easy. You can even generate questions which are not too easy for students or for anyone else learning based on the slides can answer. We can even create such Jeopardy questions, which we call, because they follow certain schemes. So I'm a scientist, my field is physics. We can use this to ask who this question is talking about. And if we go to this, we see here, that's created, generated from RDF, from the knowledge graph, from the statements we extracted from the text. So here we found Isaac Newton is a scientist. That's a bit of information I showed with Vitaly Klitschko in the beginning, who was a politician. Then we found he was born in Lincolnshire. Once again, Vitaly Klitschko was born in some city in Kyrgyzstan. And then we found Isaac Newton is a physics. So we can now, with the template behind it, generate sentences like, I'm a scientist, my field is physics, and I was born in Lincolnshire, who I am. Create such nice questions, which we can then ask students who attended the lecture, for example here about physics, or philosophy, or whatever, and then ask them what's the right answer. And then they would have to state it. Or for example, here's an interface where you can see how this looks like in an implementation of ICTERI-2018. So we ask those questions, filling in the blanks, or giving the right answer. For example, Barack Obama is a lawyer, engineer, or office holder. But here you can see already, it's not working perfectly in all cases, because the right answer would definitely also be lawyer for Barack Obama. He is a lawyer, he was a lawyer. That's a bit of the problem of knowledge graphs. They often don't see or don't look back in time or don't have this information all available. So here the distractor lawyer is not a bad, or is a bad distractor because it was actually a right answer, but he's maybe not an engineer and archaeologist, and he's an office holder, which is also a bit a strange term for president, which would not be true any longer because now it's Barack Obama. And now, looking at the knowledge graph, once again, we can see that if we generate such questions, and especially if we generate distractors, so other answers that could be the right answer, we see here that we follow the hierarchy in the graph. So we can ask for other persons. So we can ask for who is the mayor of Kiev? And then we can just look up some random persons, and if we then say, okay, give me some persons from the knowledge graph, then they would maybe propose Madonna or Arnold Schwarzenegger, but people immediately know that's not true. They can't be the mayor of Kiev. But if we go down this hierarchy, and if we go down to, in this case it's soccer players, but if we go down here maybe to Ukraine politicians, which we find in the DBpedia, then we can generate nice distractors automatically, asking for Vitaly Klitschko, maybe for his brother Vladimir, and for other Ukraine politicians who could, in principle, be major mayors of Kiev. And then it becomes much harder to answer this question. So we can control the level of difficulty of this multiple choice question by just controlling the hierarchy level of the distractors. That's the basic idea. And yeah, it works nice. As I said, sometimes there are some issues. It doesn't work for all domains, and that's important. The problem is often the domain. So that's one of the main problems. I've shown many examples on DBpedia, but if you go to specific domains, if you go to your science area, of course this knowledge is often not available. It would be really hard finding distractors for TF-IDF, what I introduced, or for other concepts which are maybe not that well covered in the knowledge graph. So current knowledge graphs are often about common sense knowledge, but not too deep knowledge. They might be deep in soccer, in movies, in certain areas where there are very detailed databases on the web. For example, about movies, you can ask all questions. That's why I asked this question about who starred in a movie together. Because this information you have, but often you don't have information, and that's why it's the limitation of all these intelligent tools and the limitation of any IBM Watson or the dialogue systems we develop at Fraunhofer is always that we don't have the proper world knowledge. So we first need the knowledge to really understand the relations. So that's all, not really, because what I forgot to introduce, and which is very important, is the human. So even if we have knowledge, if we have intelligence, if machines can create questions, I think what you learn from this talk is that the human, with his or her perceptual system, with his or her cognitive system, with the knowledge, the domain, the world knowledge we have, is still very important. And that's why I showed many visual examples. So if we think of a human with its large brain, it has a lot of context of knowledge. And in the best of the cases, really the human and the knowledge graph work together. And that's often what we call visual analytics. So it's not just about visualization and models and how they interact with each other. It's about the data and the knowledge, but it's important that there's a feedback loop, that humans maybe correct mistakes in the knowledge. that humans interpret the knowledge correctly. That's why I showed so many visualizations. I showed visualizations because humans understand visualizations. They have a great perceptual system. They're very good in pattern detection. So if you just show a lot of dots on a slide, a human will see patterns a machine might not see. So humans have certain capabilities, a lot of capabilities, which are great. And I think the idea, and that's really the idea behind all these intelligent techniques that are currently developed about autonomous driving, about Industry 4.0. I was just recently at Hanover Fair, where this was discussed a lot, so that not robots are doing all the jobs, but there's an interaction between robots and humans, there's an interaction between computers and humans, and with this interactive, I would say, symbiosis, so that you work together, solve problems together. I think that's the main point, and that's why it's important for me to stress once again, we not just need intelligent systems, we need intelligent users, and we need also visualizations, and that's why I showed them today, a lot of illustrations, visualizations, to make users understand the knowledge, to see the knowledge. It can also be generated documents, it can be timelines, it can be geographic visualizations, but of course no one can read the buttons here directly. No one can understand the data sets if they don't see the interfaces for the data sets. They have to use interfaces, they have to use applications on these data sets. They need personal assistance, tools maybe like Alexa or other speech-to-text tools, but I think the human is still the one who is absolutely important to really do a lot of clever things. Of course, cars can drive in the near future, they can drive autonomously, many production machines can work autonomously, but there are still a lot of tasks which need creativity, which need human intelligence, and that's why it's so important to also provide interfaces to this knowledge and not just expose the data. I'm saying this because I sometimes experience in the semantic web community that there are a lot of data sets made available, but if we don't have interfaces to really access those data sets, or if we don't have tools which I showed, like the Ralph Finder, where we find relations and those cool stuff, then yeah, the data's out there, but no one is using it. So consuming this data, making use of it, creating some innovative business on it, maybe making money with it, that's something, of course, which should be more in the focus, especially in business context. That's very important and crucial, and that's why we need good interfaces based on these knowledge graphs. But to recap, and that's the time now to recap the talk, we can say knowledge graphs are great. So we don't have to make them great again. They have ever been great. The problem is that they, of course, are born in academia, lead some way to the industry. They work well in many areas. For example, these examples I showed from Google, where there's common sense knowledge behind. They work great in biology, in biomedicine, in publishing actually, like these papers of the conference, all the author metadata, creation metadata, all this is knowledge which is made publicly available as a knowledge graph by Springer. Springer has a Sparkle interface that can be accessed, so that you can see maybe who published with whom. So in the end, that's a bit of a definition. I added here knowledge graph represent information in a highly structured and semantically rich form that allows for advanced querying, reasoning, and data integration, which is not that easily possible with other approaches. We have to follow this graph idea. We have to have typed links to really understand relations. Just relational tables are not sufficient often because we don't know how they relate. Here we see how they are related. So that Barack Obama is married to Michelle Obama, that she lives in the United States, that he is a politician of the United States, or was. So once again, I said outdated knowledge is a problem. He was born in Honolulu, that's still true, so he's from Hawaii. Honolulu is in Hawaii, so we have all this information about Barack Obama available in one knowledge graph, which is maybe even easier for humans to read than a text about him. Not too sure, we did some studies. It really depends a bit on the text, but this graph can easily read by humans. More complex one, maybe not, but more complex texts are also difficult. And that's maybe among the most important challenges. So we often have text nowadays. We have a lot of information, a lot of knowledge available as text. So the papers you submitted to this conference, they were text. So they were linear text. You have to follow, you have to read through the paper, you have to create the knowledge graph yourself. And actually you create something like a knowledge graph in your head. You create associations, you want to find links between things you read in the paper, you want to see how this relates to other work. Especially reading the related work is quite a lot of associations with other work. So related work sections might be even more easy to represent as a graph. You have to do this yourself, and my thesis is it would be much easier often to have already this linear text structure represented in a graph form. As I said, not visualized necessarily, you can visualize it still as a document, structured document, whatever, but having it in this knowledge graph form, you can do a lot of great stuff. You can follow related work, you can see how this relates, what is similar, what's not. You don't have to read through all the texts, which can be quite some effort. It becomes even more powerful if you enrich it with external data. And here we have linked open data, which is important, especially for scientists. So we cannot buy a lot of data, and we don't want to. We use data which is available. So recap these linked data principles. And that's what I wanted to address also, particularly in this talk. You can link to external data, you can make a lot of use, you can use natural language interfaces, but you need also some visualizations or ways to explore the knowledge. It can be natural language processing, you can talk to a system, to an agent, but as I showed, you can also use visualizations because they can be very powerful in interpreting data, interpreting graphics, interpreting knowledge. So in data science, we use a lot of visualizations because, as I said, the human perceptual system is very good in pattern recognition, is very good in analyzing data from different angles, from different viewpoints, to use whatever, this geographic, this time-based, other categories, other factors, and to focus and look at the data and then to infer knowledge from it. And I think this is, and that's back to the example, this is especially important in education. Students not just need to understand facts, because facts nowadays are not too important. You can look them up. So if you want to know what's the height of ICTERI-2018, that's not something I would like to learn. You just look it up, I just ask Google. So a lot of facts are available, or when Kiev was created, that's good to know, when it was established, or when, but you don't have to know, you can look it up. Facts are easy to look up. What's important is that you also understand the relations. And for understanding the relations, you need to link data, you need to link knowledge, you need to use and explore knowledge, and that's why it's especially important in educational context to have such interfaces where you can use and make use of the power of knowledge graphs. So knowledge graphs open many opportunities, question answering, I showed the example, you ask a question, the computer answers, information retrieval, I showed a lot of examples, so that you query for Kiev, you get results in structured form, you query for ICTERI-2018, you get results in a structured form. It allows autonomous agents, so really agents doing phone calls. There was a recent example by Google. This is, of course, some way to go still. They are usually not that intelligent, but yeah, more and more intelligent, especially these assistants which play music for you and so on. You can use them, especially in learning, as we do, because I still think just reading text is not the right way to learn. You really need to understand the relationships, and graphs and visualizations, illustrations are very important. And you can do, and that's a bit of the top of the science, of course, is to do reasoning, to do some very clever stuff, that you have machines who can play chess, that machines who can drive cars, all these things. But for doing this, you have to really make sure that the lower layers are already fulfilled. So often, if we want to do intelligent stuff, really intelligent stuff, we first need to integrate the data, we first need to structure the data, we first need to add ontologies, to add knowledge, to then do the really cool, interesting reasoning and logic on top of it. Yeah, that's it. So thanks a lot for your attention, and I'm now open for questions. If there's any. Yeah. Do you want to use the?
I can shout. Actually, my question is more related to the first part of your talk, which is a real finder. We tried to do this, and I have several questions regarding this. Can I ask?
Yes, sure.
So first question, you are working with Sparkle. Do you do incremental Sparkle writing?
In this case, no. We just have certain Sparkle patterns. But yes, we do in a way that we use results for another queries, yes. But not, we don't have full Sparkle 1.1 that so not property pass or something.
Then the second question, how do you handle the size of Sparkle query? I know that it has limitations of size, and if you write big query, it might somehow stop.
Yeah.
How do you handle this? Or is it somewhat technical? I would like to just to know for the process.
That's right, that's often a big limitation of these public data sets and the queries. So if you ask two complex queries, you get a timeout response. The server is not answering because the query is too complex. So as I personally, I would prefer asking complex queries. What we do is we break them down in really simple queries usually. So first asking, for example, about Kiev and the first, like REST first search, just looking for the entities around Kiev, not just the next ones already. So just going in the graph one hierarchy step. And then having another query who takes this, and that's why I talked about incremental Sparkle querying, who takes those first step results to query for the second layer. And you really have to be careful to break it down, and that's why we have this animation, which looks cool, but it's actually because the queries need some time to get processed. So that's why we have this animation that they were created, and you saw them popping up, because especially the more complex Sparkle queries need some time to get a response to.
It is true.
And that's definitely a problem, and that's why we use our private DBpedia endpoint, because the public one is often too slow because too many people are accessing it at a time. Yeah.
I also checked your papers, and in one of your papers you wrote that structural relationship between objects can be omitted, and you omitted subclasses and equivalents, I guess.
Yes.
What if we really need only subclasses and equivalent classes? Can we somehow change the configuration of the shell finder to search only for these two?
Yes, you can. Let me quickly check.
We can not immediately.
But just to show you where you can find it. So here there is a configuration menu. You can add it, and here you can say the ignored property. And for example, you can remove some, like the subclass of link. I'm not too sure, but I think that should already solve your problem. Otherwise, you have to go to the code.
Yes, because it seems otherwise it might be like curiosity to those subclasses.
But the nice thing, it's open, so you can catch the Sparkle queries that we send to the server by just listening to the browser communication, and then you can simply monitor the browser communication, catch those queries, and re-engineer yourself.
I see.
And create something. Problem with well-finder is it's still Flash-based because we developed it some time ago. Nowadays, I wouldn't do it in Flash because most browsers don't support any longer Flash. But we might not do another version because it's a demo.
Do you have an API?
An API?
Yes.
No. And,
why?
Because it's research work, it's a showcase, it's a demo.
It is already a working example.
It's a nice example. Maybe we do at some point, but yeah, we can discuss maybe in the coffee break. And maybe you want to design one. That's a good idea.
Can I ask one more question, please?
I'm not sure.
My question is like a philosophical one. From the presentation, I got a view that Virtuoso is going away, and now the player number one is graph databases, because you switched somehow from Virtuoso to graph database. Is it like a trend?
Yeah, it's hard to say. That's a general question, a good question. So the main point is I think there's a shift away from relational databases. And there is a change to, for example, there are many document-centric databases, NoSQL databases, and graph-based databases. I think the triple stores are still used, they are good, but they are very much, from this academic point of view, developed, and sometimes those graph databases like Neo4j are more efficient. And that's why, for practical reasons, we used it. But they're also limited. So there are several triple stores like Virtuoso, Stardog, and others, which have their pros and cons. I think it really depends a bit on the project. If you really need a very responsive, fast, then you better go for Neo4j. If you want to do more logic and want to do more clever stuff, then you need a triple store still. So it's both, but I definitely see the graph database as a result of trend of this having more graph-based knowledge representation. Yeah. Thanks.
Okay, thank you. Any other question? No? Okay. No, I have 2 or 3.
Thank you. Sorry for taking all your attention from the same research group. My question is more about the types of perception of different people, intelligent users. As we all know, there are 2 different groups of people. The first group has symbolic perception, and the second group has pictorial perception. The approach is very nice. I mean, the approach visualizing stuff from symbols to pictures is nice for the second group. What about the first group? Can you offer something for them as well?
That's a good question. From my experience, it's also something which is not yet sufficiently researched, especially in the semantic web context. So whenever I see new approaches like visual interfaces, and I've seen a lot of them, then there are some user studies, but they're often with just some students, some random students, so not really the target groups we are aiming for. That's a very, very interesting and difficult question, and I don't have a good answer to this. We looked at it a bit about gender differences also, like the mental maps, how they are created. So if I walk through Kiev, as a man, I rather tend to create a like a mental map of it, so to follow the streets. As a woman, in general, it's not it's more like a landmark approach. So I remember certain buildings. It has some biologic foundation and long evolution history reasons. I'm not sure if it's really true for everyone, but this tendency is given. It's a good question. I think those things are rather the mental map approaches, and in your case, rather the second group. For the first group, we need more interactive, explorable things where they can also maybe arrange things themselves. So put certain landmarks. I think there are far too little approaches, so that's definitely something which needs more investigation. So very good remark, and I don't have an answer like that's the right way to go. It's still missing some good visual and illustrative stuff there. Yeah.
Thank you, Stefan. It was a very informative talk. I have a question about slightly different field. For example, healthcare. I heard there are some knowledge graphs in healthcare for giving a, you can say, the abstract description of healthcare data, or specifically blood pressure data, okay, in some kind of event. So are you aware of any example in that?
Yes, if you talk about patient data, so then the problem is it's still very much nationally funded. So we have some certain initiatives in Germany where they want to represent this in a structured way. There's always a problem of privacy, and that's a major issue. It's not open data, not everyone wants to see what your diseases are. You don't want everyone to see what your diseases are. I think Scandinavian countries are very much advanced there. They are very open with the data. In Germany, there's a lot of privacy concerns. There are approaches. For example, we have in Germany now created the medical data space. We have a project where we exchange patient data and give it to the doctor. But I cannot really tell you that's the best vocabulary or told you whatever, because from my observation, it's also very national thing still. And the European solutions, there are some projects started in the Horizon 2020 investigating this, but it's still a bit of an open issue also to exchange patient data among Europe. the question is how much is this needed, because often you go to the doctor in your home country. But now, of course, if I'm now down here, it would be good if some Ukraine doctor would also have my data. But it's definitely a heavily discussed issue, and linked data knowledge graphs are an issue, but the most important is privacy and secure data exchange there, I would say.
Thank you.
Okay. Yes, last question, I think.
Don't get this. Maybe I have very formal questions, not very sophisticated. Is it possible in your concept, in your approach, to construct a knowledge graph which itself consists of the knowledge graphs? It means, is it possible to construct some hierarchy of knowledge graphs?
Yes, it's not just possible, that's really often the idea with linking knowledge graphs. There are two approaches. One is, which has been done a lot, is importing other knowledge graphs. The problem with the importing is some might disappear. So you often have broken links. Some people publish some knowledge graph and then they don't maintain the website and they disappear. That's the problem. That's why I think the trend and tendency is not to import ontologies in others, but to rather link them. And if they're not available, you just skip them and you don't have this knowledge. But if they're available, yeah, you build on this knowledge. Or, which is also sometimes done, creating mirrors. But if you create a mirror copy of it, then it can be outdated. So there are different tendencies, but that's exactly, and that's a good point, that's exactly what's the idea. Because you might have designed a very good knowledge graph in your area, and I don't want to reinvent the wheel, so I created a very good ontology graph in my area, then we link them, and then the world is much more intelligent because two people, two experts in their field have created knowledge graph. And that's exactly how it should go, yeah.
Thank you.
But maybe just one last comment. Often it's the problem, you see some other knowledge graph and you say, I'm more clever, I build a better one. That's a bit of a problem. That's why you often extend existing ones. Just use them and say, okay, maybe I model this concept differently. But it's a very good point. The problem is different word use, but the opportunity is different expertise. And if we bring them together, we are all more intelligent. That's really crowdsourcing, swarm intelligent in a way, yeah? Thanks.
Okay, so I think we finish here. I would like again to thank you very much, Stefan, for this very, very interesting talk, and thank you the audience for the questions and the attention. Thank you.
Thanks.
Just to give you a very brief hint, we have a coffee break right now. Feel free.
I think we have 3 talks in this session, and I give the floor directly to the first speaker, so he can introduce himself. 20 minutes of talk and 10 minutes of question.
Dear colleagues, my name is Ivan Izonin. I am an assistant professor at Kyiv Polytechnic National University. I would like to present the result of our research called Non-Iterative Neural-like Predictor for Solar Energy in Lviv. Authors Roman Tkachenko, Hakan Kututsu, Ivan Izonin, Anastasia Doroshenko, and Yuri Tsimbov. My presentation will consist of the following parts. Since the result of this work is some notification of new paradigms of artificial neural networks, the neural-like structure of geometric transformation model, I will describe common topology and training and using algorithms for this tool. Then I will present first modification. We call it RBF based on the SGTM. And finally, I present the second modification. We call it combined RBF and SGTM. The experimental results you can saw at the end of my presentation. The most popular modern neural paradigms are demonstrated their effectiveness in many practical tasks. They constructed on the biological analogies, and iterative learning algorithms. This determines some drawbacks and limitation of these tools. You can see that in the slide. Based on this, we're trying to find more accurate and fast methods to solve a number of computational intelligent tasks. In this presentation, as I said, the modification of the common successive geometric transformation model is presented. The SGTM is a new concept of information object modeling. It provides an effective solution to a wide range of problems. This neural-like structure realized training and self-training principles where learning and use procedure are the same type and based on the use of a common set of general arithmetic operations. This is topology of SGTM neural-like structure. Many scientists, when saw this topology at the first time, thought that it is multi-layer perceptron, but it is not multi-layer perceptron. If you stress your attention to the hidden layer, you can find the lateral connection between the neighbor neurons. We don't use existing iterative learning algorithms. We train such tool by our algorithms, which based on the successive transformation from one neuron to another. A detailed description about this tool you can find in these two books. In the chapter from the Advanced in Computational Computer Science, you can find the mathematical description of the training and learning, training and use procedure for this tool in supervised and unsupervised modes. In the chapter of Advanced in Soft Computing, you can find the solution of the problem of linear-based image scaling. Use this tool. Training algorithm. I try to explain the training procedure using a three-dimensional space of realization for the function of two variables. This function is presented there. Before that, I must explain this graphs. There are two features for one step of computation, for each step of computation. Some action and visualization of the results. The darkest blue determines the sum action. The main goal of each step of computation is to reduce the dimensionality of hyperbody due to orthogonalization and memorize the information about this reduction in the neural-like structure. Before the first training steps, initial status, all data are collected on the inputs and outputs. In the first step of training, geometrical transformations are performed in a space whose dimensionality is reduced by 1. We have only one trained neuron. After the second step, the data points are projected on a strange line perpendicular to normal vector. We have trained the second neuron in the hidden layer. Finally, all data points are projected in a coordinate region, PGP. So we got information about geometric transformation for regeneration of a training matrix. This information is used for interpolation or extrapolation approaches of vectors that didn't belong to the training matrix. In the use mode, the given input vectors of neural-like structure should reproduce output, VT1. Hidden neurons operate sequentially. Hyperbody information arises from input layer and hidden neurons to output layer, QGP. Data points on input are moving toward coordinate region. On the output, the data points are moving to the predicted values. After the second step of operation, we have the VGC. After the set step of operation, data points are learned around the coordinate region on inputs and have predicted values on outputs. The first modification of the common narrow-like structure of successive geometric transformation model is presented at this slide. We called it RBF based on SGTM. The topology consists of two parts. The first part is the common neural-like structure. The second part is this RBF input generator. Before training, we use the second part of the topology for transforming all input signal to the RBF inputs using equation 1. The output of these two are formed according to the classical representation of RBF method in a form of linear combination of the form radial inputs. This makes it possible to increase accuracy, but the main drawback of this tool is very small extrapolation properties. Therefore, we developed another modification, the second modification. It also consists of two parts. Dark blue color determines the common neural-like structure, and blue color it determines the previous topology. We combine that. We have in input layer we have initial inputs, and inputs were formed by the RBF generator. The training process of such modification is the same as previously case. Modeling was conducted on the data which was we trying to solve the prediction task. We try to predict the daily solar energy in Libya using the data which was collected from 25 cities in Libya, and the database of this data has 1,800 data vectors, and each of them has 7 input attribute characteristics and 1 output. This data was collected for the period of 6 years during the 2010 to the 2015. The sample was divided to the training and test data. We try to solve this task using existing methods. They are support vector machines and linear regression. For this purpose, we using commercial software, Orange software, version 3.8.0. The main parameters of this method are described in this feature. As you can see, we get the result, but it is not perfect. This result was obtained by using our method. First, it's a common neural-like structure geometric transformation model. This is parameters of this tool were used in experiments. It's our first modification and second modification. As you can see, we obtained the best results using our second modification, combining version of RBF plus SGTM. From this graph, we can see the previous conclusion. We get a more accurate result by using our two modifications. This is a visual comparison comparison of the result where the sketched plots B and E were obtained using our approaches. Conclusion you can see in the slide. Thank you for your attention and sorry for my English.
So thank you very much. Doesn't work. Thank you very much. We have a lot of time for questions because you were very quick. Who wants to start questions? Yes?
Why did you use example from Libya, not from Ukraine?
Because one of our co-authors, Hakan Kutuzov, has collected this data and we use them for experimental results.
Are there some recommendations of what kind should be data? This method can be applied. Are there some requirements to the input data?
This requirement is the same for all neural networks. We have some input data in a number, or we can change when we have some data from 1 to 20, we can change it to 0 and 1. All requirements for all neural networks.
My question was, you used only one data set,
yes,
and showed that this data set perfectly well for this method. Why don't you try several other data sets, maybe from Kaggle, just to try and show that even Kaggle data can be robustly applied to this method?
We have some requirements to the paper long. We have only some pages, and we have we solve many practical tasks using common tools. This to modification we developed 5 months ago, and we don't use any data. But the common version of neural structure of successive geometric transformation model provide a very good result and different tasks. Image scaling, build digital watermarks, imbalance data classification, clusterization. We try to solve a big data problem in e-commerce. We have many applications.
There is one there, and give you the microphone.
Did you use ready product software, as you said, Orange 3.8.0, or it's your own development?
We use this software only for comparison with existing methods. Our approach was developed by us. The developer was Yuri Tsenko. He developed some programs based on this mathematical tools.
Okay, and the question is, what are the future improvements will be as a result of your investigation, of your work done?
Thank you for these questions. We try to investigate all parameters of these tools for obtain the best results, to increase the quality much more than now we have 95% of good answers. I don't know in English, but we try to more increase in the quality.
Okay, thank you. Any more? Oh, one more question here.
Where did you calculate? On what machine? What are the parameters of the machine?
Any specification details for your network? Hardware configuration.
How many?
This tools is not iterative. They don't require big memory resources, big time resources, and others. We can apply any. No, I don't know the. We don't apply for bad computers for the computers which was developed 20 years ago, but for modern computers it's work.
It sounds like a silver bullet that you developed. It does not require any resource, but it provides perfectly good results. Could it be possible? It doesn't consume. What's the computational complexity of your algorithm?
We don't calculate this, and in this paper I don't present the time resources for that.
Okay, it's out of the scope of this presentation, right? Okay, thank you.
Right, I propose we stop now for this paper, and we move to the second speaker, or to Oleana Yashchenko.
My name is Oleana Yashchenko. I'm a professor at Kyiv University, Economics Cybernetics Department. And now I would like to present our investigation, estimation of production potential in various regions using popular neural network. The current development of Ukraine is characterized by inter-regional social economic disparity. Therefore, an important stage in the analysis of the development of the country as a whole is the assessment of each of the regions. This topic is relevant and often we use this because it is difficult to identify a single set of indicators that characterize the state of regional development food. There is a problem of calculating the integral indicator for the estimation and ranking of regions by level of development. The problem of disproportionate regional development is one of the most important and actual that are solved not in Ukraine only but also in the whole world. For effective public administration, it is necessary to assess the level of development of regions, to identify regions with different levels of development. Therefore, a large number of scientific papers are devoted to this field. It is proposed to apply an integrated approach to the analysis of the regional indicators contours that characterize the level of production potential. At the first stage, the normalization of indicators is carried out taking into account the economic content. The next stage is the calculation of integral indicators with three different approaches. At the last stage, the clustering of the regions by the level of production potential is carried out using Popper neural network. Application of the Popper method with the data that's clustered simultaneously allows to project multidimensional data into two-dimensional space and analyze the resulting cluster system. The economic situation of any country is largely determined by the level of development of industry and agriculture. So one of the most important groups of indicators of socio-economic development of the regions is exactly the production potential. Production potential is the maximum possible volume of output that the economy is able to produce with the full involvement of all available resources in the process of social production. The assessment of the production potential of the region is based on the analysis of its components, industrial, agricultural, and investment potential. In turn, the characteristic of the industrial potential of the region is based on the research of the following indicators: the volume of industrial products sold, the share of the region, volume of sold industrial products, and volume of sold industrial products per person. Regarding agricultural potential, its analysis is carried out on such indicators as gross crop production and gross livestock production. The investment potential in this research is characterized by an indicator of capital investment. The construction of the integral index for assessing the production potential is carried out according to the following three approaches. The first method is an integrated assessment of the competitiveness of regions. It has a hierarchical structure which consists of three types of indices: general integral index of the benefits of the region, group integral indices of various aspects of the region's life, and partial integral indices characterizing the advantages of the region. The proposed technology for calculating the regional benefits index implies the formation of databases, that is, the formation of a matrix of output data, determination of indicators of stimulant and destimulant, as well as their normalization. Calculation of the consolidated integral index of investment advantages of the region is carried out on the basis of the formula of average geometric group integral indices, which characterize its main aspects. The second technique also uses a hierarchical analysis scheme. At the stage of calculation of the group indicator from the obtained normalized indicators, it is suggested to use this formula. The third method for the evaluation of indicators offers the following formulas for indicator stimulants and for indicator destimulants. Then the value of the factor weight is calculated. This procedure consists of three consecutive steps: calculation of the product of the factor load and the share of the total dispersion that it explains, calculation of the sum of the received products of all factors, and calculation of each factor contribution to the specified amount. The next stage is the calculation of aggregate indicators characterizing certain aspects of economic development and the calculation of the integral index of economic development. Traditionally, the clusterization of regions by integral indicators, it is proposed to determine the number of groups by the Sobius formula. A powerful alternative clustering method is the use of component neural networks, component self-organizing maps, or SOM. It is the most well-known unsupervised neural network approach to clustering. Its advantage over traditional clustering technique is improved visualization capabilities. SOMs find and mapping from high-dimensional input space into the feature space of reduced dimension and make possible visualization in reduced dimension. On the initial stage of learning algorithm, we should set the weights for small random values, the initial neighborhood size, and the values of parameter function. The steps of algorithm you can see on this slide. The word clustering in general is hierarchical agglomerated clustering algorithm. On the initial stage of clustering, each node is defined as a cluster itself. At each next stage, two clusters with minimum distance between them are combined in one new cluster. Starting from the full distance matrix, lower triangle matrix, as the distance measure is commutative, at every step a row and the column is stripped, and the different row and column is updated until the matrix is completely clear and only one cluster remains. The mean and the cardinality of the new cluster built as product of the combined step is as follows. The modified sum-word clustering algorithm combines a method of displaying data using self-organizing maps with a classical word clustering algorithm. As a specialty, the distance matrix is initialized in a manner that takes into account the number of data records matching to the nodes of the map. Nodes with many matching data records are weighted stronger than nodes with fewer matching records. As distance measure, we have to use the modified word distance. This method offers its own cluster indicator, which defines the reasonable number of clusters into which the input sample is broken. The statistical data of 24 regions, excluding Kiev, for the period from 2010 to 2016, is used for estimation of the productive potential of the regions. The calculations were carried out according to three methods mentioned above. Results of ranking of regions by integral indicator of production potential are presented in next slides. The ratings that it used for comparison are based on the results of the regions in 2010, 2013, and 2016. The use of different techniques gives close results for readers and outsiders ranking. Donetsk and Dnipropetrovsk regions occupied the first and second places in the level of production potential in 2010 and 2013, and Dnipropetrovsk region is also the leader in 2016. As for the Donetsk region, it dropped to 5-6 places for the results of the use of the first and second method. The Donetsk region remained in second place for the third method. But according to all approaches, the value productive potential level for this region it has significantly decreased compared with 2013 and 2010. This is not surprising given the situation in the east of the country. The most indicators of all years show the Chernivtsi region and the Zakarpattia region. Over the research period, the following regions improved their results: Vinnytsia, Kyiv, Lviv, Poltava, Mykolaiv, Kharkiv, Cherkasy. As well as minor but positive changes had taken place in Volyn, Zhytomyr, Kirovohrad, Sumy, and Khmelnytskyi. Differences in the rating list are due to the peculiarities of constructing integral indicators. Therefore, information obtained by another method should be added to prioritized regions. There were 5 clusters allocated for 24 regions using the Stroger's formula. The table shows the clustering of Ukraine's regions by the level of production potential in 2016 for each of the 3 methods. It should be noted that for regions with average values of integral indicators calculated according to different approaches, there are significant differences in the distribution of regions by clusters and their mutual ordering. One can note that uneven division of regions into clusters. Depending on the calculation method, there are empty groups. The open and narrow network was used to verify the results and identify stable, homogeneous groups of regions. Calculations were made according to the statistics of 2016. The same indicators as in previous methods were considered. The Solvent method performed clustering of input data and calculated the clustered indicator for each of the possible cluster numbers. Figure 1. The horizontal axis of the diagram indicates the number of clusters. The vertical axis shows the indicated value for each cluster system. The diagram can be interpreted as follows. If the indicator value is high for a particular cluster system, then clustering can be considered as natural for constructed data. Accordingly, when the indicator value is low, for some cluster system, clustering is artificial. Consequently, the peaks of the cluster indicator graph represent true clustering. According to calculations, the largest indicator corresponds to 18 clusters. The next maximum is 8 clusters. But given that the number of investigated objects is 24, it is expedient to group the regions into the 8 clusters. Figure 2 shows the division of regions into 8 groups by the level of production potential in 2016. In brackets under the name of the region, the average place in the ranking is indicated by the results of previous calculations. Note that the region's leaders stand to the left side of the map, and outsiders stand to the right side of the map. The division of regions into 5 groups, figure 3, which was proposed earlier, is considered in parallel in order to compare the results. It should be noted that the indicator for such a number of clusters was very low. Clustering in 5 groups is artificial and not entirely correct. This figure presents a profile of contributions of indicators in the formation of 8 clusters. The contributions of indicators are arranged from the bottom up according to their ordering in the performed calculations and marked with different colors. The Dnipropetrovsk region is in the first place with the highest value of the integral indicator and is isolated in the C8 cluster. All cluster metrics are at levels above the average significantly. The next cluster, C7, consists of the Kiev region, which has somewhat lower levels of indicators. Vinnytsia and Cherkasy are in the same cluster, C5, which is characterized by a very high level of gross livestock production and gross crop production. One can note that on figure 3, Kiev, Vinnytsia, and Cherkasy regions form one of the 5 clusters. However, Kiev region is significantly different from the other 2 regions by the level of capital investment. Therefore, its allocation to a separate cluster is justified. Note that in figure 3, clusters C1 and C6 have been united into one cluster. Separating the last 3 regions into a separate group is logical and reasonable. The adequacy of the constructed clusterization models was verified using a dispersion analysis. For each investigated indicator, the intergroup and intragroup components of the variance were calculated and the hypothesis of the significant difference was checked. The results of the calculations confirm the quality of clustering and the level of significance of 5%. The next step, organ maps are built without taking into account the 6 regions that have ranked as the leaders. That is done in order to improve the results of conducted clustering and the allocation of stable homogeneous groups. This approach allows to reveal structural features of the aggregated regions with average values of integral indicators. The distribution of regions into 11 clusters is presented and new groups are allocated. The proximity of former regions is detected, Sum, Khmelnytsk, Zhytomyr, Ivano-Frankivsk, and so on. It should take into account the location of the region on the map compared with its neighbors, proximity to the leaders or outsiders of the main rating. And here are the conclusions. You can read it.
Okay, thank you. So we also have some time for questions. Who wants to start questions? Oh, sorry.
Thank you. Thank you for your results, for the presentation. It was interesting for us. As I understand, you used different ranking for different criterion for all regions. So in this case, how did you rank the region which has different place in for different systems which you used in this ranking? It's a first question. And second question, you talked about a factor which is stimulants and destimulants. How did you distinguish these factors, and what kind of these factors did you use? Thank you.
First of all, the criteria is the same in the first, second, third method, and for neural network also. But different only the formulas what we can use. And as for stimulants and destimulants, just a moment. So yes, we can see indicate stimulants and destimulants, but unfortunately I don't know how we do it because I don't know the technical details of this work. This is our third course.
Satisfied.
Sorry for such a question, but just now we are on the IT conference. But you said nothing about any kind of IT technology support, software solution, or for example, how you have collected this data. My questions, did you make any kind of implementation, any kind of software or information support for your thinking?
Okay. There's some algorithms, some word algorithms we find on the internet, and this is a free product for 10 days. We use it. That's IT.
Means you did not make any kind of your IT technology solution?
No, it's not our problem, because we would like to involve and use IT in economic research. We are not IT specialists, we're economists.
We are on IT conference.
Okay, what can I do?
Do we have other questions? Yeah, there is one over there.
What is the benefits of your proposed approach into comparison with traditional one, and who can apply this approach in their work activity?
The benefits, you can see that traditional methods give us an empty clusters, but it's not very convenient for investigation. But the Kochman neural network is more convenient for visualization. And for whom we did it? Now, a lot of analytics used such program products in their work, and it's very popular now.
How can you explain as an economist why Poltava is at the fourth place? It means it really has a huge potential. It's level 4, and Donetsk is 5th. What is in Poltava? Interesting that the algorithms show that it's really underestimated region.
Poltava, look at this. Crop production in Poltava, agriculture is very huge. And also maybe always sorted data points per person, maybe this factor also. But the Donetsk region now is not so good with Poltava. It's the first place we have different crops. The second place is Kiev. That's the result of our calculation.
So are you already speaking about potential, or are you using actual data? So is it the estimation of what you think should be, or is it the measure of actual data that measure the production in cities?
Northern cities are regions.
The actual measures, right? Because you call it potential. So I had the idea that it was just an estimation of what you thought would be. And then the question was, why do you measure potential? Why you may have actual data about 2010?
This is real data at that time or moment. What is the future?
I'm so curious about the details about your real data. How many parameters were in your data? What's the dimensionality of your data? What's the size of your data? Could you please give us more details on that?
The size of our data, it's not so huge.
How many records?
I think no, unfortunately, because technical details.
Okay, thank you. They're important.
Do we have more questions? No? So thank you very much again, and I guess we have to move to the third talk. So third talk is from Victoria Cosa. Oh, and there is a crash. No, it's okay.
Hello everyone, my name is Victoria Casa. I am a PhD student at the Department of Computer Science of the Norwegian National University in Kyiv. My supervisor is Professor Vladimir. I will present our research work on refining terminological situation using string similarity measures. This work has been performed together with our master students Arona Shlemenenko and Ridwan Popov, and in cooperation with Ontology Engineering Group at the Polytechnic University in Madrid. David Charles Fraga helped us extract terms from text using the European term extraction software. In my talk, I will focus on the following aspects. I will start with explaining what motivated us to study a terminological situation in document collections. Next, I will continue by presenting the background knowledge and methodology used in our work. Further, I will present our research objectives to the SWOT approach. I will then report the results of our work. After that, I will present how our evaluation experiments were set and which data were used. I will also report and discuss the results of our evaluation. Finally, I will make conclusions and also outline our plans for the future. Now I will explain what motivated us to do this research. As researchers, we have to read more than we can read. So we are always interested in what was this paper book about. For example, many of us may be curious what was the last volume of ICTERI proceedings about. Find this out, we may try to build a word cloud based on the full text of the book. For this, many of the shelf services are available. However, these do not help a lot, as you may see yourselves in this slide. One may try to build a word cloud based only on the keywords provided by the authors. This is a little bit more informative but too coarse. There is also no way to see which aspects were more or less frequently mentioned in the book. A more advanced approach is automated term extraction from text. The solutions are also available for use. You have to feed your text into the software and to receive a ranked list of terms back in the while. You have to remove the stop words, cut off insignificant terms, and further analyze the list, for example, by building a term cloud. This approach results in a more informative output, but the flat list is still too long and somewhat messy. For example, plural and singular forms are regarded as different terms. So you have to manually group, structure, and finally build a model. For example, the model like the picture on the slide shows here terms in the conceptual hierarchy. One One more important disadvantage of ICTERI is that it does not scale well. For example, imagine that you wish to learn what knowledge management as a discipline is about. In this case, looking at just one book would not be sufficient. You will need to extract tons from gigabytes of text like processing our Spring knowledge management paper collections. This collection comprises roughly 9,000 full-text papers published between 1997 and 2016 in 15 relevant Spring journals. Even if your ICTERI tool manages to extract tons from this bulk of text, it may take quite some time. Furthermore, the ranked list of retaining tons will contain hundreds of thousands entries. Hence, you have to extract a sub-collection of a minimal possible size that terminologically represents the whole collection sufficiently well. The solution for finding such a sub-collection is offered by the on-to-left methodology. On-to-left looks for a terminologically saturated subset of papers. Hence, however, on-to-left solution still returns a flat list of terms. In this list, several extracted terms may mean the same or be similar to the other. The examples are given in the slide. Such terms may be grouped in one as shown in the slide. If so done, the ranked list will be shorter and much less confusing. We also expect that if term grouping was enabled, the terms situated quicker. So a smaller number of documents are needed to form a representative sub-collection. One promising way to group terms is the use of string similarity measures. I will now outline what background knowledge is used in our research. In on-to-left, we extract a sub-collection of a minimal possible size which has statistically the same terminological footprint of the domain as the entire collection. To extract such a sub-collection, we start with an empty container, then add documents there, and stop when adding more does not add new terms. This will mean that the terminological footprint became saturated, as pictured in the diagram in the top right. For that, a sequence of dataset is formed. We take in plain text documents from the collection and put into the first dataset D1. Then a subsequent dataset is formed by adding the previous dataset to it and adding the increment of additional input documents. We do so until all the paper are not there in the last dataset D1. Then each subsequent pair of dataset term extraction is done. Terminological difference is computed between the extracted blocks of terms using the THD algorithm. Saturation is detected when, for some pairs, the terminological difference falls below individual terms significant threshold. Our objective is to make it quicker, so with less documents in the minimal representative sub-collection and less extracted terms. This is shown by the green arrow in the slide. As potentially appropriate for term grouping, we have selected the 4 string similarity measures presented in this slide. The reason for this selection are described in the paper. Jarrow measures the number of characters transformed between the strings. Jarrow-Winkler refines Jarrow by avoiding the pairs that match at their beginning for a certain length. Jacob looks at the ratio of the same characters to all characters. Sorensen dice counts the same bigrams, 2 character sequences. I will now outline what are our research objectives, hypotheses, and approach. The objective of our work is to improve terminological saturation by making it achievable on a smaller set of documents. For this, we put forward and check the following hypotheses. The use of a string similarity measure, further abbreviated as SSM, helps detect similar terms reliably and allow correct term grouping. The SSM has to be properly chosen. If semantically similar terms are grouped, then terminological saturation is achieved quicker. To find semantically similar terms, string similarity thresholds have to be set for the SSM. Of course, the use of an SSM will result in computational overhead. However, we expect that the improvement of terminological saturation will override the negative increase of computation time. We do term grouping by applying the selected SSMs in the developed similar term grouping algorithm, further abbreviated as STG. We refined the baseline THG algorithm for measuring terminological difference by applying STG, comparing terms using SSM and term similarity thresholds. We evaluate the refined THG algorithm against the baseline by trying all implemented SSM with chosen thresholds. In evaluation experiments, we check if the refinement results in better terminological situation, which SSM takes less time. These experiments help us find out if there is the best SSM for detecting terminological situation. I will now present our results and finding out what would be a reasonable threshold to distinguish between similar and non-similar terms. A threshold we look for has to help reliably distinguish between similar and non-similar terms regarding their sense. We found out that to determine such a threshold, the following four cases have to be taken into account: full positives, full negatives, partial positives, and partial negatives. In full positives, character strings are fully the same, terms are clearly regarded as similar, the same, SSMs return high values. In full negatives, character strings are very different. Terms carry different semantics and are regarded as different. SSMs return low values. In partial positives, the terms in such string are similar, though not the same. In this case, SSM return moderately high values. In partial positives, the character strings are very similar, but the terms are different in their sense. This is the hardest case to detect as SSM return high values. To take into account all the cases, FP, FN, PP, and PN, for that we developed a test set containing the pair of terms falling into different categories within these cases. For each pair of terms, all four implemented SSM were computed. Further, we looked at the average values. The test set is publicly available at the beginning. The SSM values for different categories in the four cases, FP, FN, PP, and PN, are within different intervals. These intervals are shown as colored bars in the bottom of the slide. The intervals for partial positives and partial negatives unfortunately overlap substantially. Therefore, if a threshold is chosen to filter out partial negatives, also some of the partial positives will be filtered out. We assume that partial negatives are rare in professional terminology. So we decided to use the values from the partial positives intervals for chosen term similarity thresholds. The intervals for the term similarity thresholds of each individual SSM are given in the table. These intervals have been evenly split in 4 points, mean, over 1, over 2, and max. I will now show how the baseline THG algorithm has been refined. The baseline THG developed by Tatanitseva et al. Takes a pair of bags of terms ranked by severity, as shown in the slide. If equal terms were found in both bags of terms, each computes the difference in their severities. If there was an orphan, meaning that there was no equal term in the other bags of terms, it's the severity of this orphan. Differences are accumulated in the return THG value, which stands terminological difference between the input bags of terms. Our first refinement was the introduction of the STG algorithm for term grouping. For example, STG will group the terms temporal, temporal logic, and temporal representation into temporal and modify this value by the average of Z3. STG is run before running THG. This is how the baseline THG is implemented. The refinement shown in rounded rectangles was first the addition of the two parameters SSM and term similarity threshold value, the addition of the term similarity check in line 7. I will now present how was our experimental evaluation setup and performed. We use time document collection as our evaluation dataset. Time document collection contains the full text papers of the proceedings of the time representation and reasons for their series. The collection contains 437 full-text papers published between 1994 and 2013. These papers have been pre-processed manually, including their conversion to plain text and cleaning of these texts. We have chosen the increment for generating the dataset to be 20 papers. So we have generated 22 incrementally enlarged dataset D1, D2, D22 using our dataset generator. The objective of our experiments was to find out if using the refined THD algorithm yields quicker terminological saturation compared to the baseline THD algorithm. We also looked at finding out which SSM best fits to measuring terminological saturation. The dataset created from the time document collection have been fed into both the refined and the baseline THD algorithms. All the computation have been run on a Windows 10 64-bit PC with the specification shown in this slide. We applied the refined THD 16 times, one per individual SSM and per individual term similarity threshold, and the baseline THD one time. The values of absolute terminological difference, the number of retained terms, and the time taken to perform term groupings by the STG algorithm in seconds were measured in every experimental run. Terminological difference measurements revealed that the refined THD algorithm detected terminological saturation faster than the baseline THD algorithm, no matter what was the chosen SSM or term similarity threshold. If the results for different measures are compared, then it may be noted that the saturation curves look differently, depending on term similarity threshold point. Overall, the use of the Sorensen dice measure demonstrated the least volatile behavior for different term similarity threshold points. All implemented SSM coped well with retaining significant terms. It is indicated by terminology contribution peaks. Please see diagram D for the max threshold point at the top right. It shows that all the SSM curves follow the shape of the baseline THD curve quite closely. They have the peaks exactly at the same measurement points where the baseline has. Sorensen dice demonstrated the best ratio of retained to all extracted terms, as shown in the diagram at the bottom right. Using SSM in measurement terminological difference increases the computational complexity quite substantially. The time spent also goes up with the increase to the term similarity threshold value. Sorensen dice and Jacquard, however, more stable to the increase of the term similarity threshold than Jarreau and Jarreau-Wainwright. Sorensen dice takes roughly an order of magnitude more time than Jacquard. We ran the baseline THD and the refinements using the first individual SSMs, and as shown in the table regarding the criteria listed at the left. Overall, and a bit surprisingly, Jacquard SSM was the one that demonstrated the best performance. I will now conclude and outline our plans for the future. We researched if using a string similarity measure for term comparison and grouping improves terminological saturation. For finding this out, we choose the 4 SSM based on the specific of term comparison, developed the test set of specific term pairs to decide about the term similarity threshold for these measures, implemented these measures, the algorithm for similar term grouping and the refinement of the baseline THD algorithm. Cross-evaluated the refined THD algorithm against the baseline and also all SSM against each other. Gave our recommendation about the use the Jacquard measure in the refined THD algorithm as it demonstrated the best performance in our experiments. Our future work is planned as follows. Firstly, we plan to check if the results will be similar on the other document collections. For that, the same experiments will be repeated on the dataset generated from our DMKD and DAC collection. Secondly, we plan to improve the performance of the Sorensen dice measuring implementation. Its high computational overhead is the only shortcoming against Jacquard. Thirdly, we will explore if a similar John grouping algorithm will be good for grouping features and including feature taxonomies. This task is on the agenda for the second conceptualization phase of OnToWeb. Thank you very much for your attention. I will now be happy to take your questions.
Thank you very much. So perfect timing. So we have quite some time for questions.
Thank you for your presentation. So you talked about saturation of terms from some volumes of series Springer, and I would like to know, did you choose some terms, what kind of these terms, how many of these terms, or it's a new future research? Example.
It's example.
But did you have some examples of saturated terms from this research? Or not?
Yeah, from the start.
Thank you.
So yeah.
Yeah, the bigger terms. Here. There. Just to let her relax a little bit. First thing to mention was that the data set you mentioned was the wrong data set. We used the time collection, not the Springy DMKD collection. Secondly, this slide demonstrates the top of the ranked list of saturated terms, which is temporal time, temporal logic, interval model, and so on. And the significance values are given to the right column. That's it. Of course, you may have all the data, not only the top, in the links given in this presentation.
Thank you.
Just a short question. What I did not understand is how do you detect that similar or the same texts have different meanings? Are you using ontology or thesaurus or something like that for this? Well, it's not loud enough.
I can speak louder if you want. The question was, how do you detect different semantics? Where are the semantics stored? The last line, the third way I read, how do you detect that the semantics are different?
Sorry for interrupting, it was a real difficult question. Thank you for that. Perhaps the presentation was good, wasn't it? So we did not really detect different semantics. We just produce hypotheses, pointing out that in these four cases, full positives, full negatives, partial positives, and partial negatives, there are some thresholds indicating that it might be a different semantics. That's it. We do not measure any semantics in there because we do not have this information. We just have simple flat strings with a very, very moderate size. So measuring as many semantics from such a small piece of data is really impossible. This is a raw estimation by putting appropriate thresholds on the stage. That's it.
But why not checking against the ontology?
Because in that case, it will never become a scalable approach in terms of computational complexity.
I also have very small two questions. First, very, very technological questions maybe. you have elaborated some approach to text analysis, to language processing. My question is, in which kind of real-life applications is this approach useful? For example, software requirements specification, or maybe speech recognition. My question is, in which real information can be used this approach?
Maybe, for example, you have a big document collection, and this approach was used extract a sub-collection minimal documents to read and...
Once again, you now explain me the, let's say, some example how to use it. My question is, once again, very technology oriented. We are talking about information systems at this conference, yes? Yeah. In any case. I ask you, which kind of information system, information retrieval system, information recommendation system, or something like, for example, advanced requirements management system. You know about this system, yes? Maybe in such system, is it really useful, is it good to use your approach? Maybe you have to make some ideas about this question, yes? And second one, simple questions. Is your approach to this text processing related to some language? It means now you are talking about English, for sure, in English language, yes? For example, we have some Russian language or Ukrainian language. In this case, do you have some, or will you have some differences in your approach?
In future.
No, maybe this approach is independent on the language. From this formal definition, from this, let's say, measurement, or this approach is dependent on some language.
I think it's implemented for other language.
Independent. Yeah. Fine.
Well, we have more questions. So if there is no more questions, then I suggest we close the session. So we are a bit ahead of time. You have more time for lunch. Then thank you very much for attending, everyone, and see you this afternoon.
Many thanks, Frederick.
Symbiotic University Enterprises Corporation in Ukrainian game industry, Volodymyr Shestuk and Maria Zhenikova. Please approach you first. So I remind our event. You have 25 minutes for your report, and it's about 5–10 minutes for discussion.
The topic of the report is building an extensible university enterprises cooperation in Ukrainian game industry. Game industry in Ukraine is developing dynamically and becoming more attractive for many international game industry companies. However, the preparing specialists in game industry is quite complicated because of deficiency of narrowly focused specialists such as game graphic designers, sound designers, story
storytellers, content managers, etc. On top of it, there are no necessary software and hardware in Ukrainian universities for preparing specialists in game industry. So there is a gap between educational supply and the demand of game industry market. Given all these problems have stipulated the initiating International Erasmus Plus project, University Enterprise Cooperation in Game Industry in Ukraine, Game Hub project. The goal of Game Hub project is to develop infrastructure which allows students to improve their skills and competencies needed to work in game industry and intense cooperation between universities and enterprises. Game Hub has 4 main components. They are as following: pedagogical component, which includes methodology for learning the students, ATO veterans and unemployed people how to create games. Technological component, which includes creating and maintaining the work of game laboratory. Methodological component and informational component. The main goal of Game Hub project is to develop infrastructure which allows students to improve their skills and knowledge in game development. Our report dwells on the development such this infrastructure in Kherson National Technical University. Our university is a member of international consortium of Game Hub project. The target audience of Game Hub in KNTU contains retraining students of the Institute of Postgraduate Education, students of the Faculty of Cybernetics and System Engineering, teachers and trainers who wish to use the gaming technology in the educational process, engineers interested in training and improving skills in the game development, and unemployed persons, ATO veterans, and applicants from the Regional Employment Center. The principles of Game Hub in Kherson National Technical University are as following: adaptation of educational programs to labor market requirements, close cooperation with game enterprises at the regional, national and international levels, gamification of the educational process, combining teaching with practical work, intensive cooperation with partner universities, and using the advanced innovative educational methods and techniques. There are some priorities of Game Hub in Kherson National Technical Universities. Implanting new gaming technology in the educational process, training within the specialization computer games development, collecting and updating the educational resources, mastering the skills of game content creating for the learning process, implementing the research and development in the educational process. The pedagogical component of Game Hub in Kherson National University consists of 2 stages. Monitoring the competencies needed for game industry market and developing these competencies. To monitor the competencies, a survey among the specialists from game industry enterprises has been conducted. This survey, the analysis of the results of this survey shown us the list of competencies needed for game industry market. This list consists of such competencies as creativity, academic integrity, ability to work in the team, problem solving, etc. And the analysis of this survey shown that the students of information technologies department don't have the necessary skills and knowledge to meet the requirements of game industry market. So the existing curricula and educational programs should be adapted to the new list of to develop the new list of competencies. The methodological component of Game Hub in KM2 is based on developing the learning models. Some our teachers passed special trainings and developed learning models aimed at developing the necessary competencies for required by game industry market. The technological component of Game Hub in Kyev National University is based on creating and maintaining a game learning laboratory. This laboratory has all necessary equipment, software and hardware to develop necessary competencies. The academic component of Game Hub in Kyev National Technical University is based on the creating computer games design educational programs for software engineering, training programs, development of computer games for the Institute of Postgraduate Education, and also developing training models for the university's curriculum and for the retraining course. These models are developed by Kyev National University Work Group, and 15 training models developed by our partners. To provide sustainability of Game Hub in KM2, some conditions should be fulfilled. The first condition is maintaining the game learning laboratory. The second condition is trainings for teachers delivered within the project. These trainings lead to professional advancement of our teachers and developing learning courses within the project, and all these conditions leads to training the skills and competencies matched to the international labor market in the game industry area. To control the development of a learning model, the piloting was provided about 150 teachers and about 500 students were trained using the developed models. Based on the results of piloting, the models should be corrected and adapted. The results of pilot should be ready by the end of May. Here you can see the roadmap of Game Hub in KM2, and here you can see the conclusions. Mutually beneficial and sustainable university enterprises cooperation can achieve a better match between competence profile of university graduates and those required by game industry. This will provide graduates with high-level employable skills, and Ukrainian graduates will meet the requirements of the international labor market. Thank you.
Thank you. So, please, what questions do you have? So, maybe my question. So, you talked about competences of students who take part in this program. Who prepare these competences? What representatives of employers propose requirements to the competences of graduates of such program?
Thank you for the question. A survey has been provided among the specialists in game industry in the enterprises, in game industry enterprises of Kherson area, and the results of this survey show us the list of competencies required by game industry market.
As we know, competences, it's a basic, then you propose your learning outcomes and courses. You demonstrated courses which was divided into two parts. One part you propose as which will teach your partners. Who will your partners? Who teach students in this program?
We have some Ukrainian universities, our partners. Our partners are Kharkiv Polytechnic University, Kiev University, and there are some universities, and each university prepared learning models in the area of game industry, in the area of game development. And these models are open educational resources, and we can share our models between our universities and prepare our students using our models and models prepared by our partners.
Did you have IT company who propose you, for example, tasks or practices or requirements to students in this field?
Yes, we have some IT companies. We communicate with them, and they helped us to complete the list of competencies, and they help us to develop laboratory tasks, laboratory works for our students based on the tasks which are required for developing these competencies.
Okay. You talked about specialization in this course, so you have a specialty and students who choose this specialization. What academic rights did you have?
Maybe my colleague can help to answer this question.
How students can choose study program, and computer game development is a study program on the first level for labels, and for the second level for masters. So they can graduate with this study program.
Okay, but as I understand, students who have specialization can have some academic rights. For example, they can developers of games, for example, in this industry or something else, as additional, supplementary to their basic specialty.
Yes, yes. And we have some enterprises who want to employ our graduates with these competencies.
It's a Ukrainian company or international IT company?
in the frame of our project, we have some communications with companies abroad.
Okay, you talked about bachelor degree and master degree, and you talked about possibility of such specialization for both types of them. So what difference between them? It's the same program for them, or there is some difference between them?
Yes, there are some differences. On the bachelor level, they can have basic competencies for developers. And on the master level, they can obtain some competencies in research and development more than basic.
What types of the games did you develop with your students?
All types of games.
Maybe some examples of them?
Some of our graduates now work in game development companies at the international level, and they took part in producing the most popular games. But they start in the university, and then they develop the ideas.
Okay, and maybe last my question about gamification in your educational process. How did you build such gamification process for your students? What does it mean in your sense?
This is additional part of the project, and we have provided some trainings for our teachers and trainers to develop their skills for using games in education. Gamification is a very interesting subject in Europe, and some of our work group members have ability to see this process in Spain, in Austria, and we want to have this ability in Kherson National Technical University. So we select a group of teachers and we train them to develop educational games.
Okay, and maybe do you have a different level of complexity maybe for your tasks in the games?
Some teachers from IT, but some teachers from mathematics, physics, and the level is.
Okay, thank you. Maybe other questions?
So what I've heard, I'm sorry, I wasn't from the very beginning. It's like a program sponsored by somebody, like a game industry, from Ukraine game industry, to have places to train future developers of games. And Kherson, Odessa, Kiev, and Kharkiv were chosen as a spots. Is it true like you are like a place that you train the future game developers because of the somebody's order, or somebody came to the university and say we would like to have proper programmers of games. We are willing to pay you, teachers, to train for us future game programmers. It sounds like wow. It is cool. There are 4 universities in Ukraine that really teach how to code games. Is it the only benefit? So the only benefit obtained who then takes these people, these graduate students to work? Is it purely commercial idea, or is there some budget funding involved? I mean, who is the founder of this genius idea, just to train game developer from the very first course? It's really
Who found this?
Who gave this money?
This is single sponsor plus project, so the European Commission pay money for this idea.
It's inside Ukraine.
Inside Ukraine, yes.
Isn't it strange?
But we prepare specialists for international game industry market.
This is European added value.
Yes.
We train developers for Europe, Western.
So, and abroad of Ukraine, in European countries, there is same program for game developers, and you can use the experience to do same inside Ukraine. Okay, it's a very good experience and very interesting and very good diversification of IT specialty for our country. Thank you. Our next paper number 10, analysis of ICT application in technology transfer management within Industry 4.0 conditions, education-based approach. Olga Prokopenko, Olga Kudrina, and Vitaly Onymenko.
So, dear colleagues, dear class, let me present you the results of international study which is devoted to the evolution of ICT application in technology transfer within the higher education institutions. Here you see the main points of our study. The first point deals with the education technologies and the evolution. Here we should talk about the demand-driven approach. So within the industry 4.0 conditions, business enterprises or government sectors need for new kinds of specialists. And so education systems in any country needs to change its structure, its approach, its ideas, and so on. So within this we consider the technology transfer. In Ukraine, generally in legislative base we consider technology transfer in its limited idea. So it's only the trade some innovations from the higher education institutions or academia to enterprises. But generally in developed countries the technology transfer is more wide. When we consider it, we propose to apply the idea of lean startup. So it means that the enterprise and higher education or academic institutions cooperates closely from the early stage of product to create some new excellent idea and realize it to improve the competitiveness of enterprise. At the same time, Industry 4.0 also transforms as business models in enterprises, and so we need to improve technology transfer. And in this case, the ICT, or Information and Communication Technologies, play a critical role. And so, finally, we propose to consider the integrated approach. It's a business to education, B to AE, and education to business, E to B linkages. So, here you see the basic definition of McKinsey Corporation of Industry 4.0. From this definition, you can see the main critical role of ICT, new kinds of ICT. In Ukraine, we apply these technologies in a very limited cases, in a very limited number of enterprises, and less in the academia and higher education institutions. The next 3 points creates new conditions of rapid innovation management and search for new ideas. And so, in this case, the higher education institutions can find it's a very important place. In the previous presentations, we have already considered the game industry, and only for the last years, the higher education institutions in Ukraine are involved in this process. So it's one of examples when the startup approach will be applied in the higher education institutions, because the game industry is a very it's an industry with high profits. So here we have defined the main conditions of future engineering education development. So the first point is interdisciplinarity of innovations. Today, in the first presentation of our conference day, we have considered some maps of ideas, some visualization, and so in this case it's very important, because already when we will analyze the publications in scientific journals, or we analyze the components of some high-tech products, for example iPhone, we will consider the combination of ICT, nanotechnologies, and so on. So the next is adaptability. I have already talked about the rapid innovation process, and so higher education systems and every person, user or developer, need to adapt to new conditions. Other points here are connected with the first and the second. So, in these conditions, ICT is very important, because through the ICT we can create interdisciplinary innovations, especially through the some simulation tools. We all know that nanotechnologies couldn't appear without simulation, because if we conduct all experiments in practice, we will spend a lot of money and time, and through the simulation we can create new materials and only then create them in practice. This approach is already used in the space industry. It's a simulation of creation of materials. It's a generally approach. The next, lifelong learning. Here ICT also plays a very important role, and lifelong learning is a tool of adaptability of any person. The next here is coding based. Today, in the first presentation of our conference day, we see how using the simple code we can create some analytics tools, strong analytic tools. And today analytics becomes a new kind of profession. We can find analytics in financial sector, in government sector, and education sector, and in other sectors. And so for this we need to know a coding base. Then the next here is a culture of interaction. When we talk about some calculations in the international level. We all hear about clusters, space sectors, innovation networks. So we need some tool to communicate, to exchange data, to process data, to communicate with the results and so on, to manage projects. The example here can be a international space station. And now this approach is disseminated in other sectors. Leading IT companies within their strategies promote, for example, approach for coding for children. So they understand that the higher education system is not efficient in the new conditions, and so they are working to create young innovators and then to work them in the future. We can name here Lego, Apple, Parrot drones, and so on. Within this, children are learning to code some drones, some innovations in construction, and so on. So, how could we catch this Industry 4.0? First of all, we need an appropriate national strategies. Here you see a list of national strategies of some leading countries and of some developed countries and developing countries. Unfortunately, Ukraine only working fragmentally within the Horizon 2020, and we have already heard about it. But in the National Innovation Strategy, National Innovation Development Strategy, there is no ideas about the Industry 4.0. The same we can say about the education strategies development. It's very dangerous and it can create some threats for national security in future, because we can lose some capacity for development, because we are moving in the Industry 4.0 age, and we have a chance to destroy the innovation gap between the Ukraine and developed countries. This chance appears only once for 30 years, and now we are in this moment. When we're talking about the higher education strategy, technology transfer strategy, we propose to consider situational approach. So we propose to develop a strategy for every higher education institution or academic institution. For these purposes, we propose to consider education foresight methodology. Generally, foresight was were used in technological sectors, but now this methodology are used to consider the impact of new technologies on other sectors. So here you see the key points of our ideas. So the first here is a technological trajectory. When we are talking about some technical or classical university, we need to consider how the technologies are changing over the world and what we can do in our university to create new products for transfer, how we can communicate with business as domestic business, both with international business. The next here is a technological package concept. When we talk about some high-tech products, we need to consider it as a combination of technologies. I have already talked about the iPhone. Here we see nanotechnologies, optics, ICT, and so on. When we're talking about university or some state or country, the key point is to find some place in the global value chain. We all know that the high-tech products are produced, components of high-tech products are produced in different countries, and so we need to find our place. We can realize it through some international project. Today we have here about the computer games through the Erasmus Plus project and so on. So we need to find some possibilities for development. And ICT here plays a very important role because it allows communication, marketing of innovations, and so on. Here you see the structure of foresight methodology application for any university. It's a universal scheme because within it we analyze the key technologies, the key areas of our specialization, and we analyze how what decisions we need to improve our competitiveness in this area. And according to this, we build our strategy. To consider the role of ICT technologies in the university, we have proposed such evolution model of university. So when we are talking about Industry 4.0, we can consider University 4.0. And our suggestion is based on 3 criteria. So it's digitization, integration, research and development in the education process, and cooperation with business. These components are the main factors of world-class university development. It's a Stanford University and others. All these components are necessary for development of products of Industry 4.0. I have already talked about the startup approach, lean startup, so it's a closely cooperation from the early stage of product, and also it's a creation of some components of product and product evolution. So we need to improve our project almost every day. Here we can know about technology. And the same will be the characteristic of all products of Industry 4.0. And so we need to change our strategies. When we are talking about the university, we can consider cooperation with business as a source of ideas and development resources, especially the financial resources, which is very important for Ukrainian conditions. For the Industry 4.0, we propose to consider such main characteristics of technology transfer. I have already named some of them, but the main here is digital and virtual engineering. So it can help to save some resources and can help to promote the marketing of innovations through the international innovation networks, some presentations, and so on. And it is necessary for Ukrainian conditions because the equipment of labs of our domestic university is not very good. And sometimes it's a critical situation. And so we need to develop some ideas and then promote it and to find a customer. Because the idea is a new resource is the main resource of Industry 4.0. We all know that almost every startup is started from the zero in resources, but there is only idea. And then some partners help to realize it. To realize all suggestions, we propose to consider ICT-based higher education strategy. Here we have included the main characteristics of technology transfer, and the main characteristics of Industry 4.0. Within the ICT-based strategy, we propose to consider common tasks and some tasks that are oriented on the competencies of Industry 4.0. Common tasks, they are, in some Ukrainian universities, they are already realized, in some they are in some critical situation, but generally, as you can see, these tasks are oriented to support the general education tools. It's a library, university management, data exchange, some labs, equipment, and so on. And the non-traditional skills, within this we propose to promote the skills that are relevant for Industry 4.0. So it's a digital design, ability to communicate, ability to manage ideas, and so on. In order to realize this strategy, we propose to consider the ICT package of university. Here we have shown the main competencies of Industry 4.0 and some ICT tools which are useful to promote these competencies. When you look on this list, you can see that these technologies are not used in Ukrainian university. Maybe some knowledge management systems, but for example, customer management systems are not used, and so it creates some problems, especially for startups development. For the conclusion, here you can see the main points of ICT application strategy in university. Here we tried to combine all characteristics of Industry 4.0 and to consider the tasks of technology transfer. For Ukrainian conditions, we understand that the jump for Industry 4.0 ICT conditions for Ukrainian university is not possible, and that's why we propose to realize the evolution strategy through the projects. And within this project, we propose to consider such a list of tools. So, this idea is based on the suggestions of Luxembourg Center of European Reforms, and so for the developing countries they propose to create some simple projects, and when these projects are successful, they recommend to disseminate them to other institutions. And so we think that this approach will be useful for Ukraine. Thank you for attention.
Thank you. So, your questions, please. My first question. You talked about relations between business and education, B2E and B2B, on the first of your presentation. So, tell us, please, what difference and what common size between B2E and, for example, B2B or B2C in the as traditional, for example, process of e-commerce? What difference between these two processes?
Thank you for the question. I have told that for Industry 4.0, the main resource is ideas. And so the communication E to B and B2E is based on ideas. So when the enterprise needs to have some problem, it can go to university and ask to help. Of course, if the university has a customer relationship management, it has a marketing of innovations, and enterprises know what the university can do. From the other point of view, the relationship E to B is a classical task of technology transfer, because every innovation created in the university should be implemented in practice. In Ukraine, we have a great number of patents or other intellectual property, especially the intellectual property for program products, but they are not used because they are created without market analytics, so they are not necessary for enterprises, and even if they have some market capacity, the enterprises don't know about them because we have no marketing of innovation. And that's why we propose to consider this task. Also, when we will look on the, for example, Stanford University, for this university, even such term or as innovation ecosystem was proposed. So it means that around the university a great number of enterprises is created, and they are developed based on the ideas of this university. And this has a great capacity for Ukraine, where we have almost 200 universities, and we can talk about the transfer of technological technologies, both transfer of social technologies, because in Ukraine we don't even talk about the social technologies. And in this case we have the problems in the information security, mental security, mental diseases, and so on. And when, for example, the pedagogical university, humanitarian university also can be involved in the B2E and E2B relations.
Did you have some experience in proposing, for example, startup or some type of firms to have some grant to prepare, for example, it for commercial uses?
Yes, I have such experience. I have been working for 3 years as a manager of technology transfer at Sumy State University, and we have organized some promotion actions for the developments and innovations of this university, and even enterprises from the Middle East have come to Sumy and have concluded license agreement for some granulation equipment. So it's a complicated task, but there is a few international technology transfer network, for example, Enterprise European Network. We also have found two partners from European countries through the Enterprise European Network, and Ukrainian enterprises and universities can put their technological proposition in this system from their for the few years.
Thank you. Other questions? So, thanks a lot for your interesting presentation. In this section we have 2 presentations, so we close this section. Thank you for your attention.